Long before the first dinosaurs roamed the land, our planet Earth was a very different place, shaping the conditions that would one day give rise to these magnificent creatures and their eventual dominance. To understand why dinosaurs came to dominate Earth, we must first journey back hundreds of millions of years to explore the world that preceded them. We are traveling to a vast expanse of time, known as the Paleozoic Era, which began roughly 541 million years ago and lasted until about 252 million years ago. The Earth at this time was entering a phase of dramatic change and diversity, one that laid down the foundations for all future life, including dinosaurs. This era witnessed remarkable geological processes, climatic shifts, and biological innovations. It's essential to immerse ourselves in this earlier world to grasp the full canvas upon which dinosaurs would eventually paint their spectacular story. The early Paleozoic oceans teemed with life, but life on land was just beginning to stir. At the start, Earth's continents were not separated as they are today. Instead, vast shifting land masses gathered and dispersed in slow geological dances. Early in this era, the supercontinent Gondwana dominated the southern hemisphere, while other land masses like Laurentia and Baltica drifted in the northern regions. These continents continually shaped and reshaped Earth's surface due to the relentless forces of plate tectonics. The atmosphere itself was evolving. In the nascent stages of the Paleozoic, oxygen levels were climbing, thanks in large part to primitive photosynthetic organisms such as cyanobacteria and early algae. This increase in atmospheric oxygen created more favorable conditions for the emergence of more complex, multicellular organisms. Much like a carefully set stage before a grand play, oxygen was weaving an invisible web that would soon support a rich tapestry of terrestrial life. As the Cambrian period unfolded, around 541 million years ago, life in the oceans exploded into a dizzying array of forms in what is famously known as the Cambrian explosion. Trilobites scuttled across the seabed, early mollusks and arthropods flourished, and strange creatures like anomalocaridids prowled the waters. This burst of biodiversity marked one of the most profound leaps in life's complexity. Yet, this aquatic extravaganza primarily remained confined to water, with no terrestrial beasts to speak of. By the late Ordovician period, roughly 450 million years ago, some of the first tentative steps of life onto land began. Primitive plants, non-vascular, moss-like species, started colonizing damp shores and riverbanks, pioneering the move from water to land. These early plants adapted to harsh terrestrial conditions, a crucial evolutionary experiment that set the stage for the colonization of land by increasingly complex organisms. Soon after, the Silurian period heralded the arrival of early vascular plants and some of the first arthropods capable of terrestrial life. Small, armored creatures such as early scorpions and millipede-like myriapods explored the new frontier above water, breathing air and navigating rocky landscapes still sparse and challenging. These early conquerors of dry land were the pioneers, gradually transforming inhospitable environments into habitable niches. Moving into the Devonian period, roughly 419 to 359 million years ago, we observe a crucial transition that set in motion the evolutionary path to dinosaurs. The Devonian is often called the Age of Fishes due to the explosion of fish diversity in the ancient seas. More importantly, it also witnessed the emergence of the earliest tetrapods, four-limbed vertebrates, capable of moving on land. These organisms, like the famous Tiktaalik, possessed both gills and primitive lungs, and their fin-like limbs showed early adaptations for supporting their bodies in terrestrial environments. Concurrently, vast forests of primitive trees and ferns proliferated, shading the land in lush greenery and transforming the climate and atmosphere. This flourishing plant life not only increased oxygen production, but also contributed organic matter to soils, fostering complex ecosystems. By the late Devonian, ecosystems were far more intricate, with a burgeoning diversity of amphibians and a gradual shift towards vertebrates better suited for life on land. Meanwhile, the climate was fluctuating, with a tendency toward cooling and episodes of glaciation. Such environmental stress sometimes triggered mass extinction events, but life persisted and diversified. As we step into the Carboniferous period, about 359 to 299 million years ago, the Earth was dominated by extensive swampy forests comprised of giant lycophytes, horsetails, and ferns. These verdant wetlands would eventually turn into vast coal deposits, remnants of ancient biomass that informs much of our modern energy resources. The atmosphere during this time saw oxygen levels soar to nearly 35%, far higher than today, enabling some remarkable biological feats. One striking result of this oxygen-rich environment was the evolution of enormous arthropods. Creatures such as the dragonfly-like Meganeura, with wingspans over 2 feet, and massive millipede relatives like Arthropleura thrived. These oversized invertebrates were unlike anything seen before or since, filling ecological roles on land with remarkable success. Vertebrate life also flourished in these carboniferous habitats. Amphibians diversified and became dominant predators and herbivores, while a lineage of early reptiles emerged, small, agile, and capable of laying eggs on land. This ability to reproduce away from water was a major evolutionary breakthrough that would later prove pivotal for the dominance of the reptiles, including dinosaurs. Intriguingly, the Earth's continents were continuing their slow drift. By the late Carboniferous and early Permian period, around 300 million years ago, these landmasses were converging towards the assembly of the supercontinent Pangaea. This massive landmass altered global climate patterns, creating vast arid interiors and drastically reshaping habitats. The Permian period, about 299 to 252 million years ago, was a time of both flourishing diversity and growing environmental challenges. Within terrestrial ecosystems, the ancestors of modern mammals and reptiles proliferated, filling various ecological niches. Synapsids, a group sometimes called mammal-like reptiles, were dominant herbivores and predators. These Permian landscapes were complex. Wide deserts, seasonal climates, and varying vegetation types characterized by conifers, cycads, and seed ferns. The atmosphere remained dynamic, and oxygen levels fluctuated, influencing the physiology and evolution of terrestrial organisms. However, this period ended with the greatest mass extinction in Earth's history, the Permian-Triassic extinction event, roughly 252 million years ago. This catastrophic event wiped out over 90% of marine species and an estimated 70% of terrestrial species. The aftermath created ecological vacuums and new evolutionary opportunities. It is within this framework, Earth's geological and biological history spanning the Paleozoic Era with its oceans, skies, forests, and evolving creatures, that dinosaurs began their ascent. The world before dinosaurs was marked by incessant change, grand experiments in biology, and profound environmental shifts. It was a crucible of life, a planet in flux, molding the canvas on which the age of dinosaurs would soon be painted. Understanding this ancient context, life's first tentative steps onto land, the rise of early reptiles, climate oscillations, and the great reshaping of continents, helps us appreciate why dinosaurs were remarkably equipped to seize their place. The stage was truly set, in ways both subtle and profound, for the reign of these extraordinary animals that would come to dominate Earth for over 160 million years. As we transition to our next exploration, we will delve deeper into the mass extinctions that punctuated Earth's history, clearing the way for new life forms, including the ancestors of the dinosaurs. These cycles of destruction and renewal tell us much about resilience, adaptation, and the incredible story of life on Earth. But for now, let us hold this vast primordial world in our minds, a fitting prelude to the saga that is about to unfold. Mass extinctions have long acted as pivotal turning points in the history of life on Earth. These catastrophic events, characterized by widespread and rapid losses of species, reshape ecosystems and open doors for new forms of life to flourish. To comprehend why dinosaurs ultimately came to dominate the planet, it's essential to explore how mass extinctions punctuated the ancient biological drama, both extinguishing the old and facilitating the rise of the new. Throughout Earth's deep past, there have been several mass extinctions, but among the most significant are the Big Five, which transformed the trajectory of life on our planet. Each of these extinction events cleared vast swaths of ecological niches, abolished dominant groups, and allowed resilient survivors to radiate into new roles, often fundamentally changing the face of life. The cascading effects of these events highlight resilience amid upheaval and the evolutionary dynamism that followed. The first of these major extinctions occurred near the close of the Ordovician period, about 444 million years ago. Triggered by a brief ice age and associated sea level fall, this event led to the loss of roughly 85% of marine species, including many brachiopods and reef builders. Given that life was largely confined to oceans, this extinction dramatically altered marine communities. In the vacuum left behind, diverse new life forms radiated into the niches, continuing the evolutionary expansion of complexity and specialization. Moving forward to the late Devonian period, approximately 372 to 359 million years ago, another mass extinction event unfolded. This prolonged crisis occurred in multiple pulses and deeply affected marine ecosystems, with reef-building organisms suffering devastating losses and many fish lineages also affected. The causes were complex, involving changes in ocean chemistry, climate fluctuations, and possible anoxic events, periods when oxygen levels plummeted in deep waters. Though terrestrial ecosystems were less impacted, this extinction shaped the rise of early amphibians and the eventual terrestrial vertebrate fauna. The third and most renowned extinction is that at the end of the Permian period, about 252 million years ago, often termed the Great Dying. It was by far the most severe mass extinction, eliminating more than 90% of marine species and roughly 70% of terrestrial vertebrates and invertebrates. The possible causes are multifaceted, involving massive volcanic eruptions in Siberia, climate destabilization, ocean acidification, and a collapse of ecosystems worldwide. The destruction wrought by this event is almost incomprehensible, extinguishing entire groups and reshaping the biosphere in profound ways. But it was from the ashes of this devastation that the stage was set for the rise of dinosaurs. The Permian-Triassic extinction cleared away many dominant reptilian and amphibian lineages, creating ecological opportunities. Surviving archosaurs, relatives of the dinosaurs, began to diversify and adapt to the new world, capitalizing on niches once held by other groups. The Triassic period that followed the Permian extinction was a time of evolutionary experimentation. With many previous competitors wiped out or diminished, the ancestors of dinosaurs, along with early relatives of modern crocodiles and other reptiles, radiated across the shrinking supercontinent Pangaea. These early archosaurs displayed a variety of life strategies, setting the evolutionary foundation for what would become the Age of Dinosaurs. Later, at the end of the Triassic period, Another extinction occurred around 201 million years ago. Though not as devastating as the Permian extinction, this event eliminated many large amphibians and early competitors to the dinosaurs. The causes are still debated, but might have included volcanic activity associated with the breakup of Pangaea and consequent climate disruptions. This event further tipped the evolutionary scales in favor of the dinosaurs, enabling their rapid diversification and expanding ecological dominance during the Jurassic and Cretaceous periods. Between these extinction events, the Carboniferous and Permian periods demonstrated how ecosystems waxed and waned, often influenced by large-scale environmental changes. Fluctuations in climate, oxygen levels, and geography led to cycles of radiation and decline, constantly reshaping biodiversity. These dynamic conditions favored organisms capable of adaptation and innovation, traits that would characterize the dinosaur lineage. Importantly, mass extinctions highlight the interplay between chance and resilience in evolution. While many species vanish during these cataclysms, some survive due to physiological traits, ecological flexibility, or mere luck. These survivors then seize the opportunities that arise when vast numbers of competitors and predators vanish, radiating into new forms and roles. Dinosaurs were among these remarkable survivors and beneficiaries, emerging stronger as new rulers of terrestrial ecosystems. With each extinction, Earth's biosphere is effectively reset, pushing life onto unforeseen paths. The rise of flowering plants, mammals, and even humans in much later periods are all contingent upon earlier extinctions clearing ecological space. Thus, mass extinctions serve not only as moments of destruction, but also as engines of evolutionary renewal. As we contemplate these monumental upheavals, it's clear that dinosaurs did not simply appear in an empty world. They were the products of a complex, often violent history of extinction and recovery. Understanding these patterns of loss and resurgence lets us appreciate the resilience and adaptability necessary for dominance. As we now move forward into the specific details of the Permian-Triassic extinction, the greatest extinction event of them all, we will explore how this cataclysmic moment irrevocably transformed life on Earth and unlocked pathways that would ultimately lead to the rise of the dinosaurs. This juncture, more than any other, marks the dawn of a new era, where the foundations for dinosaurian supremacy were laid amidst chaos and survival. As we stand on the threshold of the Mesozoic Era, the age of dinosaurs, it is vital to understand the profound cataclysm that forged the world in which they would rise: the Permian-Triassic extinction event. Often called the Great Dying, this event, occurring approximately 252 million years ago, represents the most catastrophic biodiversity loss in Earth's history and serves as a grim but crucial preamble to the dawn of dinosaurs. Before the Great Extinction, Earth's biosphere was thriving with complex ecosystems spanning oceans and continents. The Permian period, the last of the Paleozoic era, was dominated by diverse life forms, including the synapsids, often referred to as mammal-like reptiles. These creatures, which would ultimately give rise to mammals, were abundant and diverse, ranging from small insectivores to massive herbivores and formidable predators. The planet was a rich patchwork of life, with vibrant forests of seed ferns, conifers, and cycads cloaking the land. However, the Earth was far from stable. Geological evidence indicates that the late Permian was a time of intense environmental stress. The supercontinent Pangaea, a colossal landmass consisting of nearly all Earth's continents stuck together, created harsh continental interiors subject to extreme temperatures and arid conditions. At the same time, massive volcanic activity was taking place in what is now Siberia, known today as the Siberian Traps. These enormous eruptions unleashed vast quantities of lava, ash, and gases over hundreds of thousands of years. But what exactly made this extinction event so devastating? A combination of factors likely converged. First, the volcanic eruptions emitted colossal amounts of carbon dioxide and methane into the atmosphere. These greenhouse gases triggered a runaway warming effect, a massive spike in global temperatures that upended climate regimes. Evidence from sedimentary rocks and isotopic analyses suggests ocean temperatures soared, and the warming disrupted atmospheric and oceanic circulation. Second, the elevated carbon dioxide also caused ocean acidification. The marine ecosystems, rich with corals, brachiopods, ammonoids, and other marine invertebrates, suffered as the acidity impaired shells' ability to form and survive. At the same time, oxygen levels in the oceans plummeted, leading to widespread anoxia, oxygen-deprived zones deadly to most marine life. Terrestrial life suffered greatly as well. The intense warming and disturbed weather patterns likely led to droughts, reduced vegetation, and desertification in many areas. Plant communities that had flourished began to collapse, affecting herbivores dependent on them and cascading upward through the food web. The scale of extinction was staggering. Up to 96% of marine species perished, and an estimated 70% of terrestrial vertebrate species vanished. Entire groups like the trilobites, which had survived for millions of years, finally met their end at this boundary. Many dominant amphibian lineages also disappeared, and some synapsid groups were decimated. Yet, amid this apocalyptic scenario, certain lineages managed to survive. Mammal precursors, small amniotes, and notably, some archosaur ancestors. These survivors occupied ecological refuges or possessed physiological and behavioral traits that conferred resilience, such as burrowing habits or tolerance to low oxygen. This survival would prove to be pivotal. The post-extinction world was one of ecological vacancy, a canvas with most large and dominant species wiped away. This created evolutionary opportunities for the survivors. Ecosystems were initially impoverished, but gradually, as climates stabilized, they began to recover and diversify again. One of the most consequential shifts was the rise of archosaurs, a group that includes the ancestors of crocodiles, pterosaurs, and, importantly, dinosaurs. Archosaurs thrived in the aftermath, exploiting the ecological vacuum left by wiped-out competitors. Their adaptive versatility, efficient locomotion, and respiratory systems allowed them to flourish in the radically altered environment. The aftermath of the Permian-Triassic extinction also saw the restructuring of food webs, with new herbivorous and carnivorous lineages evolving to fill niches. This evolutionary radiation set the stage for the Mesozoic ecosystems, eventually dominated by dinosaurs. In addition, the climatic conditions of the early Triassic, immediately following the extinction, were themselves extreme. Evidence points to repeated temperature fluctuations, persistent aridity in many regions, and recurring environmental stresses. These conditions forced life to adapt rapidly, favoring innovations in physiology and behavior. It's important to understand that the Permian-Triassic extinction was not a momentary event, but a prolonged crisis, possibly extending over tens of thousands to hundreds of thousands of years. The broad temporal scale and intensity of environmental change meant that recovery was slow and uneven. Reflecting on this grim chapter, we grasp how extinction, destruction, and chaos paradoxically sow the seeds of renewal. The Great Dying reshaped life on Earth drastically, but also allowed new evolutionary trajectories. Among them, the rise of dinosaurs, a lineage poised to become Earth's dominant land animals for over 160 million years. Thus, the Permian-Triassic extinction event is the crucial dividing line between the ancient Paleozoic world, rich with synapsid dominance, and the new Mesozoic world, where dinosaurs hold primacy. As we proceed, we will explore how, in this post-extinction world, early dinosaur ancestors began their journey, setting in motion one of the most extraordinary tales in the history of life. Emerging from the shadow of the Permian-Triassic extinction event, the Triassic period marks a profound new beginning in Earth's biological history. Spanning roughly from 252 to 201 million years ago, this era was characterized by ecological rebuilding, evolutionary experimentation, and the nascent rise of a group whose legacy would dominate for over 160 million years: the dinosaurs. To understand why dinosaurs flourished, it is crucial to explore the Triassic world and the early ancestors from which these remarkable creatures evolved. The Triassic landscape was unlike anything we see today, yet it laid the foundations for many modern ecosystems. The supercontinent Pangaea still dominated the globe, shaping climatic patterns and biogeography. Vast interior deserts stretched across the landmass, interspersed with fertile river valleys and coastal regions. These environments created a tapestry of habitats where ancestors of dinosaurs, as well as various other reptiles and amphibians, adapted and diversified. In the aftermath of the Permian-Triassic extinction event, terrestrial ecosystems were initially sparse. The decimation of dominant groups such as large synapsids, primitive amphibians, and many invertebrates left many ecological niches unoccupied. This ecological vacuum provided a unique opportunity for new life forms to radiate and experiment with different evolutionary strategies. It was within this crucible that early archosaurs, the larger group from which dinosaurs emerged, began to diversify. Archosaurs appeared during the late Permian or earliest Triassic and quickly spread into various ecological roles. Unlike their predecessors, archosaurs exhibited several advantages. Upright limb posture allowed for more efficient locomotion, openings in their skulls, called antorbital fenestrae, reduced skull weight, and a more advanced respiratory system enabled greater stamina and activity. These anatomical innovations gave archosaurs enhanced mobility and endurance, traits that would be central to dinosaur success. Among archosaurs, the group that would eventually give rise to late Triassic dinosaurs is known as the dinosauromorphs. Early dinosauromorphs like Marsuchus and Lagerpeton were small, agile creatures, less than a meter in length, adapted to a cursorial lifestyle with elongated limbs for running. They lacked many of the full dinosaur characteristics, but reflected the direction evolution was taking. Their success set the stage for the first true dinosaurs to evolve. The earliest true dinosaurs date to the middle to late Triassic, around 230 million years ago. Specimens such as Eoraptor and Herrerasaurus from South America represent some of the most basal dinosaur species. Eoraptor, a small bipedal omnivore, showcases a blend of primitive and derived traits. Herrerasaurus, slightly larger and more carnivorous, reveals early adaptations for predation with sharp teeth and powerful jaws. Dinosaurs in the Triassic were an assemblage of generally small to medium-sized animals, yet they rapidly diversified into bipedal carnivores, omnivores, and herbivores. This diversity indicates a swift evolutionary radiation, likely fueled by the new ecological opportunities and their physiological innovations. At the same time, dinosaurs were not the only reptiles on the scene. The Triassic world featured a wide array of reptilian contemporaries, including the crocodile-line pseudosuchians, various prehistoric amphibians, and some early mammal-like ancestors. Many of these groups occupied ecological niches dinosaurs would eventually dominate. Yet, dinosaurs were slowly increasing in numbers and ecological importance. A significant factor in this rise was the dinosaurs' erect posture, which contrasted with the sprawling gait of many contemporaneous reptiles. This limb arrangement allowed for improved locomotion efficiency and endurance over long distances, ideal traits for expanding across the vast Pangean landscapes. Moreover, the Triassic was a time of climatic extremes and environmental volatility. Seasonality was pronounced, with dry interior regions juxtaposed against wetter coastal zones. These conditions likely favored animals with adaptable physiologies and behaviors, including early dinosaurs, who were possibly endothermic, or at least had higher metabolic rates compared to other reptiles of their time. This would have given them advantages in activity levels, growth rates, and survival in fluctuating environments. Fossil evidence from the Triassic indicates that early dinosaurs coexisted with various other archosaurs, including etosaurs and Rauisuchians, many of which were large and dominant predators or herbivores. Despite competition from these formidable archosaurs, dinosaurs steadily increased in abundance and diversity. Their smaller size, agility, and metabolic advantages may have allowed them to exploit niches less accessible to their larger rivals. Intriguingly, the geographic distribution of early dinosaurs suggests that South America and parts of what is now Africa were important centers of early dinosaur evolution. The vast connected landmass of Pangaea allowed organisms to disperse widely, promoting gene flow and diversification. By the end of the Triassic, dinosaurs had evolved into two primary groups: the Saurischia, which includes the carnivorous theropods and the gigantic, long-necked sauropodomorphs, and the Ornithischia, mainly herbivorous dinosaurs with distinctive hip structures. This split laid the groundwork for the incredible diversity of dinosaur species that would populate the Jurassic and Cretaceous periods. The close of the Triassic period also witnessed another extinction event, less severe than the Permian-Triassic, but impactful enough to further reduce competition for dinosaurs. This event, linked to volcanic activity associated with the initial rifting of Pangaea, eliminated many competitor groups, particularly large amphibians and most early crocodilomorph predators. The diminished competition allowed dinosaurs to further dominate terrestrial ecosystems. In summary, the Triassic world was one of dynamic evolutionary transformation. It was a world recovering from cataclysm, where resilient archosaurs diversified and innovated. Early dinosaurs arose not as dominating giants, but rather as small, versatile creatures poised to exploit the changing environments and vacant ecological niches. Their anatomical and physiological traits set them on a path toward ecological dominance. As we continue our exploration, this understanding of the Triassic provides essential context for examining how the shifting continents and climate patterns of the Jurassic period would further shape the dinosaurian world and support their extraordinary evolutionary success. The story of dinosaurs would be incomplete without understanding the restless movements of Earth's surface beneath their feet. Plate tectonics, the slow, inexorable shifting of massive slabs of the Earth's lithosphere, played a fundamental role in shaping the landscapes, climates, and ecological opportunities that allowed dinosaurs to rise and diversify. To grasp their dominance fully, we must explore how these colossal geological processes reconfigured the planet's face during the Mesozoic era. Plate tectonics is the grand mechanism driving the movement of Earth's continents and ocean basins over millions of years. The Earth's outer shell is divided into several large and numerous smaller plates, drifting atop the viscous mantle below. These movements reshape continents, forming mountain ranges, ocean basins, and creating barriers and corridors for species migration and evolution. The fragmentation and assembly of land masses set the stage for biological evolution by influencing climate patterns, habitats, and isolation of populations. At the dawn of the Triassic period, all major land masses on Earth were fused into the supercontinent Pangaea, This immense landmass spanned from pole to pole, encompassing nearly all terrestrial environments in a single continuous expanse. Pangaea's vast size brought particular climatic and ecological conditions. Interior regions away from coasts were characterized by extreme seasonal temperatures, scorching summers and frigid winters, along with widespread arid deserts. These dramatic contrasts created challenging habitats that tested life's adaptability. The sheer scale of Pangaea affected rainfall distribution. Large desert belts formed because moisture-laden winds had difficulty penetrating far inland. Yet, coastal areas and mountainous regions received enough rainfall to sustain lush forests, enabling ecological diversity even within this massive landmass. As the Triassic progressed into the Jurassic period, Pangaea began to fragment. The forces of plate tectonics initiated rifting, tearing the supercontinent apart along developing fault lines. This breakup unfolded over tens of millions of years, with the nascent Atlantic Ocean opening between what would become North America and Africa, and other ocean basins widening. These geological shifts drastically reshaped habitats and ecosystems. The fragmentation of Pangaea into smaller continents introduced new coastlines, increased shallow epicontinental seas, and altered atmospheric and oceanic circulation patterns. These changes moderated the previously harsh continental climates and created more varied, stable environmental conditions. With expanding coastlines and shallow seas, marine ecosystems flourished, while land became segmented into smaller biogeographical units, allowing species to diversify through geographic isolation. This continental drift had profound effects on dinosaur evolution and ecological distribution. Isolation of land masses created opportunities for distinct dinosaur faunas to evolve independently in what are now South America, North America, Africa, Europe, and Asia. This continental provincialism is evident in fossil records showing distinctive dinosaur assemblages across separate land areas. Additionally, the breakup increased habitat complexity by creating mountain ranges, rift valleys, and varied terrain through tectonic uplift and faulting. Mountain-building events, such as the early phase of the Rocky Mountains and the formation of ranges in Europe and Asia, fashioned elevational gradients that produced diverse microclimates. This environmental heterogeneity encouraged specialization and speciation among dinosaurs as they adapted to different niches. The breakup of Pangaea also played a vital role in the radiation of the flowering plants in the later Mesozoic, influencing dinosaur diets and evolutionary trajectories indirectly. Varied continental configurations affected temperate zones and rainfall patterns, contributing to the patchwork of plant life from which herbivorous dinosaurs drew sustenance. Volcanic activity associated with plate boundaries further influenced Dinosauria's world. As plates rifted and subducted, volcanic arcs and flood basalts emerged, periodically altering climate through greenhouse or cooling effects. These episodic geological disturbances sometimes triggered local extinctions, but also stimulated evolutionary innovation by reshuffling ecosystems. The movement of plates not only shaped physical landscapes, but also served as corridors or barriers for migration. For example, land bridges briefly connected continents, allowing dinosaur species to spread and interbreed, mixing genetic material and advancing diversification. Conversely, oceanic barriers that developed with widening seas isolated populations, leading to distinct regional lineages and biodiversity hotspots. The breakup culminated during the Cretaceous period, with continents approaching their modern positions. By then, the resulting mosaic of island chains, shallow epicontinental seas, and mountain ranges created varied ecological theater for dinosaurs. This complex geography facilitated the remarkable diversity of dinosaur species, from gargantuan sauropods roaming vast floodplains, to agile theropods stalking lush forests. In conclusion, plate tectonics was far more than a geological backdrop. It was a dynamic architect of dinosaur evolution. The assembly and fragmentation of continents sculpted climates and environments, dictated migration routes, and fostered isolation that promoted speciation. This continuous reshaping of Earth's surface set the stage upon which dinosaurs rose to prominence, thrived, and diversified. As we proceed to explore how the climate and atmosphere of this transforming world influenced the greenhouse conditions dinosaurs inherited, keep in mind the vital role that these tectonic processes played. They framed the very environment to which dinosaurs had to adapt, survive, and ultimately come to dominate. As we journey deeper into the Mesozoic era, it becomes evident that the climate and atmospheric conditions prevailing at the time played an indispensable role in shaping the ecology, diversity, and dominance of the dinosaurs. The world that these creatures inherited was markedly different from what we experience today. A true greenhouse Earth, with elevated temperatures, higher carbon dioxide levels, and a dynamic atmosphere that influenced ecosystems and evolutionary trajectories. Understanding this greenhouse world is fundamental to appreciating why dinosaurs thrived for over 160 million years. Following the Permian-Triassic extinction event, the early Triassic climate was austere and fluctuating, marked by unstable temperatures and widespread aridity in many regions. However, as the Triassic progressed, Earth's climate steadily warmed, driven in large part by volcanic activity and increased atmospheric greenhouse gases like carbon dioxide and methane. The breakup of the supercontinent Pangaea further influenced climate patterns, introducing more complex regional variations, but generally maintaining a warm and humid environment. Geological and paleobotanical evidence attest that atmospheric carbon dioxide concentrations during much of the Mesozoic were significantly higher than modern levels. Estimates suggest levels ranged from 2 to 10 times higher than present-day values. This CO2 enrichment contributed directly to greenhouse warming, increasing global temperatures. Average temperatures were considerably warmer, even at polar latitudes, where evidence shows temperate climates supported diverse flora and fauna. There is little evidence of Earth experiencing polar ice caps during most of the Mesozoic, resulting in elevated sea levels and the expansion of shallow inland seas. The climate during dinosaur times was characterized by reduced annual temperature and seasonal variability. While deserts remained abundant, especially in continental interiors, with vast arid regions under Pangaea's influence, coastal and higher latitude regions enjoyed warm and often humid conditions. Such climatic stability and warmth facilitated year-round plant growth, creating abundant food resources for herbivorous dinosaurs. Forests dominated by conifers, cycads, ferns, and ginkgos thrived, forming lush habitats that supported complex food webs. Importantly, the continuously warm temperatures and high levels of atmospheric oxygen, although generally not as high as during the Carboniferous, provided physiologically favorable environments. These conditions likely influenced dinosaur metabolism, growth rates, and activity levels. The warm climate allowed dinosaurs to be active for longer periods, possibly facilitating higher aerobic metabolism compared to cold-blooded reptiles of today. This metabolic edge may have been essential for their success in diverse environments. The elevated CO2 atmosphere also promoted rapid plant growth, but with different vegetation compositions than modern ones. Gymnosperms were dominant, and flowering plants had yet to appear in significant numbers until the late Jurassic and Cretaceous. Such plant assemblages influenced dinosaur dietary adaptations. For instance, many herbivorous dinosaurs evolved specialized teeth for processing tough, fibrous gymnosperm vegetation, while others experimented with different feeding strategies to exploit the diverse plant life. Furthermore, The greenhouse state led to expanded shallow epicontinental seas, creating transitional ecosystems between land and sea. These coastal environments offered rich feeding grounds and migration corridors for some dinosaurs and their contemporaries. The atmospheric conditions also influenced the distribution of wet and dry climates, fostering biomes ranging from dense forests and floodplains to dry woodlands and deserts. This heterogeneity allowed dinosaurs to occupy varied niches, from massive sauropods grazing in lush river valleys to armored theriophorans patrolling drier uplands. As the Jurassic period unfolded, gradual increases in oxygen and further tectonic activity enhanced climate complexity. Periods of volcanic activity occasionally introduced disruptions such as acid rain and short-term cooling, but these did not overshadow the general trend of a warm and greenhouse-dominated world. Climate modeling and fossil isotope analyses support the idea that the Mesozoic greenhouse conditions created a relatively equable climate, meaning lesser temperature extremes between the equator and poles than today. Such widespread warmth and moisture expanded habitable zones far toward polar regions, allowing dinosaurs to live in areas that are today frigid or uninhabitable by large reptiles. During the Cretaceous, the greenhouse effect intensified further, setting the stage for even greater dinosaur diversity. This period experienced some of the highest carbon dioxide concentrations in Earth's history, which correlated with the rise of angiosperms, flowering plants. This botanical revolution influenced herbivorous dinosaur adaptations and ecosystems profoundly. The sustained warm climate likely contributed to rapid dinosaur growth rates and gigantism seen in many Jurassic and Cretaceous species. Higher temperatures increase metabolic rates energetically favorable for large bodies, as long as water and nutrients are sufficient. This environment also promoted extended growing seasons and reproductive output. It is worth noting that climate fluctuations did occur, including episodes of warming spikes and coolings, volcanic winters, and sea level changes. Such fluctuations could have driven evolutionary pressures, selecting for flexible behaviors, physiological plasticity, and diverse life histories within dinosaur populations. Overall, the greenhouse world that dinosaurs inherited was one of warmth, moisture, stability, and elevated atmospheric CO2. These conditions fostered lush vegetation, widespread habitats, and climatically favorable niches that enabled dinosaurs to grow, diversify, and roam across most of the globe. As we move forward into exploring dinosaur evolutionary advantages such as warm-bloodedness and metabolism, keep in mind the critical stage this climate set. The legacy of Earth's greenhouse period provided the environmental context and challenges that shaped the remarkable adaptations and strategies dinosaurs employed in their long reign. As the age of dinosaurs unfolded against the backdrop of a warm and ever-changing Mesozoic world, one critical aspect of their biology set many of them apart from other vertebrates: their metabolism and thermoregulation strategies. While the exact nature of dinosaur metabolism remains a subject of fascinating scientific debate, it's clear that these evolutionary advantages in energy use and temperature regulation played a pivotal role in their rise to dominance. To place this into context, it helps to understand that modern vertebrates broadly fall into two categories regarding metabolism: ectotherms and endotherms. Ectotherms, such as most reptiles and amphibians today, rely heavily on external sources of heat to regulate their body temperature. Their activity levels fluctuate with ambient temperatures, often limiting their endurance and speed during cooler conditions. Endotherms, including birds and mammals, generate heat internally through metabolic processes, maintaining stable and higher body temperatures that support sustained activity and higher energy output even in variable environments. For many years, dinosaurs were imagined as slow-moving, cold-blooded reptiles, similar to modern lizards. However, advances in paleontology, comparative anatomy, and biochemical analysis over recent decades have dramatically reshaped this view. A growing body of evidence suggests that at least many dinosaur species had metabolic rates intermediate between ectothermy and endothermy, a physiological condition sometimes referred to as mesothermy, or even fully endothermic metabolism, especially among theropods closely related to modern birds. What evidence supports this? One clue comes from bone histology. The microscopic structure of dinosaur bones reveals patterns similar to those of active, fast-growing animals. Dinosaurs, especially large species, exhibit rapid growth rates consistent with high metabolic activity. Growth rings in bones, akin to tree rings, show continuous or seasonally modulated growth, rather than slow, sporadic growth typical of many cold-blooded animals. Further evidence arises from isotopic analyses of fossilized bones and teeth. Ratios of oxygen isotopes can reflect body temperature regulation independent of the surrounding environment. Studies of some dinosaurs indicate relatively stable and elevated body temperatures, implying internal heat generation rather than mere reliance on external warmth. Moreover, the evolutionary link between theropod dinosaurs and modern birds suggests that the physiological traits underpinning endothermy were present at least in that lineage's ancestors. Feathers, once thought to be exclusive to birds, have been found in numerous dinosaur fossils, likely initially serving insulation or display purposes, further supporting a thermoregulatory role. Warm-bloodedness offered several adaptive benefits in the Mesozoic greenhouse world. Metabolically active dinosaurs could remain continuously alert and mobile, hunting, foraging, and defending themselves regardless of time of day or weather. This endurance allowed them to exploit a wider range of habitats, including cooler or more variable climates where ectothermic competitors might have struggled. It also facilitated faster growth and development. Juvenile dinosaurs could grow rapidly to sizes that reduced vulnerability to predation, enhancing survival rates and population stability. High metabolic rates supported the energy demands of active behaviors, social interactions, and potentially complex reproductive strategies. However, this metabolic advantage was not equally distributed among all dinosaurs. Some groups may have been more cold-blooded or relied on behavioral thermoregulation, such as basking or habitat selection, while others adopted higher metabolic rates. The balance of these strategies allowed dinosaurs to exploit diverse ecological niches effectively. It's also worth considering how metabolism intersected with other physiological traits. For instance, the respiratory systems of dinosaurs, particularly saurischians, like theropods and sauropods, exhibit features suggesting efficient oxygen exchange similar to that in birds. Air sacs invading their skeletons reduced respiratory dead space and contributed to a lightweight but strong body structure, enabling sustained activity and supporting gigantism. Furthermore, improvements in cardiovascular systems and limb postures enhanced oxygen delivery and locomotion efficiency, linking metabolism closely with physical adaptations that reinforced dinosaur success. In sum, the evolutionary advantages related to warm-bloodedness and metabolism provided dinosaurs with the energetic flexibility and endurance to dominate their ecosystems. These internal physiological traits, whether fully endothermic or an intermediate mesothermy, were integral to their capability to radiate into myriad species and adapt to varying climates and ecological challenges. As we reflect on these metabolic innovations, it becomes clear that the story of dinosaurs is as much about internal biological evolution as it is about external environmental shifts. With this understanding, we set the scene for examining specific anatomical adaptations that further distinguished dinosaurs and elevated them in the complex web of life during the Mesozoic era. As we deepen our exploration into how dinosaurs ascended to dominance, it is essential to trace their lineage back to their predecessors, the archosaurs, and examine the key adaptations that distinguished dinosaurs from their reptilian relatives. Archosaurs, a diverse clade that emerged in the late Permian and rose to prominence in the Triassic, encompass not only dinosaurs but also pterosaurs and crocodilians. Within this vast group, dinosaurs carved out unique evolutionary paths, acquiring distinct anatomical and physiological traits that laid the foundation for their long reign. Archosaurs possessed several hallmark features that set them apart from other reptiles, including specific skull openings called antorbital fenestrae and mandibular fenestrae, which lightened the skull without sacrificing strength. They also exhibited thecodont dentition, where teeth are set in sockets, enhancing bite efficiency and teeth replacement. Importantly, early archosaurs displayed an erect posture with limbs held more vertically beneath the body, a critical innovation that allowed more efficient locomotion compared to sprawling reptiles. These features collectively provided archosaurs with advantages in mobility, feeding strategies, and respiratory efficiency. Building upon this framework, the first true dinosaurs evolved key adaptations that further refined their abilities and ecological potential. One of the most notable traits involved modifications of the pelvic structure, differentiating dinosaurs from other archosaurs. This included changes in the hip socket that allowed for a more upright posture and locomotion primarily on two legs, setting the stage for bipedality, agility, and versatile movement. Dinosaurs exhibited a unique arrangement of limb bones that facilitated erect, energy-efficient gait, allowing them to sustain longer activity periods with enhanced speed and endurance. This adaptation was critical for a landscape where quick response to predators and prey was a determinant of survival. Another defining characteristic was the development of elongated metatarsals and digitigrade posture, walking on their toes rather than the full foot, which increased stride length and agility. Such locomotive refinement likely contributed to widespread exploitation of diverse terrestrial niches, from swift predators to massive herbivores. The skeletal architecture of dinosaurs also included pneumaticity, air-filled spaces within bones, primarily noted later in saurischian dinosaurs like theropods and sauropodomorphs. This reduced body weight without losing strength, enabling larger body sizes and better respiratory efficiency through air sac systems, analogous to those in modern birds. This efficiency underpinned increased metabolic rates and activity. Cranial adaptations played an essential role as well. Many dinosaurs developed heterodont dentition, with varied tooth shapes specialized for different dietary needs, from sharp, serrated teeth for slicing meat in theropods to broad, grinding teeth in herbivores. The evolution of complex jaw musculature allowed more effective food processing, directly influencing diet and survival. One fascinating innovation involved changes in sensory organs and neurological capacity. Although relatively small-brained by mammalian standards, many dinosaurs had enlarged olfactory bulbs and optic lobes, indicating heightened smell and vision, key to hunting, foraging, and social interactions. The acquisition of feathers or feather-like structures, initially for insulation or display, marked another monumental evolutionary leap in certain dinosaur groups. Feathers suggest a thermoregulatory adaptation linked to metabolic advancement and paved the way for flight in avian dinosaurs. Internally, dinosaurs likely possessed more advanced respiratory systems, including unidirectional airflow similar to birds, which allowed efficient oxygen exchange and supported high-activity metabolisms. This contrasts with the tidal breathing seen in most modern reptiles and conferred stamina and endurance benefits. Reproductive adaptations also contributed to their evolutionary success. Unlike amphibians needing aquatic environments for egg-laying, dinosaurs, as amniotes, laid tough-shelled eggs on land, safeguarding offspring in diverse and often dry habitats. Some exhibited nesting behaviors and possible parental care, enhancing juvenile survival rates. Collectively, these anatomical and physiological innovations, efficient upright locomotion, skeletal pneumaticity, advanced sensory and respiratory systems, specialized dentition, and reproductive strategies, enabled dinosaurs to exploit terrestrial ecosystems with an unprecedented range and efficiency. This accumulation of key adaptations transformed them from obscure Triassic forms into ecological powerhouses by the Jurassic and Cretaceous periods. They could forage, hunt, and reproduce effectively across varied environments, from arid deserts to lush floodplains. Our understanding of these adaptations also underscores the dynamic interplay between evolutionary pressures and environmental opportunities. The physiological benefits intertwined with the changing Mesozoic landscapes, climates, and biota, facilitating the vibrant diversification and widespread dominance of dinosaurs. As we proceed, the development of bipedal locomotion will offer an in-depth look at one of the most fundamental adaptations underpinning dinosaur agility and success. The tale of how dinosaurs stood tall and moved with such efficiency intertwines anatomy, behavior, and environment, revealing yet another chapter in their extraordinary evolutionary journey. In considering the vast success and dominance of dinosaurs, one of the most remarkable evolutionary breakthroughs was the development of bipedal locomotion, the ability to walk, run, and maneuver primarily on two legs. This adaptation not only transformed how dinosaurs moved across their environment, but also unlocked ecological opportunities that helped establish their supremacy on land. To fully appreciate this, we must examine both the anatomical foundations and functional advantages of bipedalism, as it emerged early in the dinosaur lineage. Bipedalism did not arise in isolation, but rather as a gradual evolutionary response to shifting demands of environmental exploration, foraging efficiency, predator avoidance, and hunting strategies. Its roots lay deep within their archosaur ancestors, who already started developing more upright limb postures compared to the sprawling gait of many earlier reptiles. However, it was among the earliest dinosaurs, and their close relatives in the Triassic period, that bipedal locomotion became a distinctive and widely adopted mode of movement. Anatomically, the transition to bipedalism involved several coordinated changes. Forelimbs became smaller and lighter relative to the powerful and elongated hind limbs, freeing the front limbs for other specialized functions, such as grasping, display, or balance. The pelvic girdle adapted to support the weight transferred to the hind legs, with the ilium elongating to anchor large, powerful leg muscles. The knee and ankle joints evolved for greater stability and range of motion suited to upright, striding locomotion. The dinosaur spine also developed curvature and muscular arrangements that aided balance during bipedal movement. The tail, long and often stiffened by ossified tendons, acted as a counterbalance to the forward weight of the head and torso. This dynamic balance system allowed dinosaurs to lean forward during rapid movement without toppling. Beyond the bones, muscle structure and tendon elasticity played essential roles in efficient bipedal mechanics. Strong hind limb muscles provided propulsion, while flexible tendons stored and released elastic energy during running, reducing metabolic costs. Such adaptations enhanced speed and endurance, crucial for both predators and prey navigating diverse Mesozoic landscapes. Functionally, bipedalism offered several ecological advantages. For carnivorous theropods, it enabled the use of forelimbs as tools for grasping or slashing prey while maintaining swift movement on hind legs. The elevated posture improved the field of vision, making it easier to spot prey or predators from a distance. Mobility on two legs facilitated more agile turns, bursts of speed, and efficient long-distance travel. Herbivorous dinosaurs also benefited. Early ornithischians and some saurischians could adopt facultative bipedalism, walking on all fours while grazing but rising on two legs to scan for threats or access higher vegetation. This versatility allowed them to adapt their posture to diverse environmental and behavioral contexts. Bipedalism also influenced social and behavioral aspects. Being upright aided visual communication with expanded ability to display feathers, crests, or other ornamentation. Such displays could serve in mating rituals, dominance contests, or group cohesion, fostering complex social interactions. The fossil record provides compelling evidence of bipedalism's early adoption. Trackways, the preserved footprints left in ancient sediment, showcases stride length and gait consistent with bipedal locomotion in Triassic dinosauriforms. Skeletal remains, including limb proportions and joint structures, further affirm this evolutionary trend. Moreover, bipedalism laid the groundwork for eventual diversification into tremendous sizes. While gigantism is often associated with quadrupedal sauropods, early giant theropods remained bipedal, relying on powerful hind limbs for locomotion. This demonstrates bipedalism's fundamental role across various dinosaur clades. Over time, some groups reverted or evolved fully quadrupedal forms, especially as body size increased and weight-bearing demands shifted. Even so, bipedal ancestors left enduring legacies in skeletal architecture, muscle attachment sites, and locomotor strategies. In summary, the development of bipedal locomotion represents a multifaceted evolutionary innovation that shaped dinosaurs' physiological capabilities, ecological versatility, and behavioral complexity. It enhanced mobility, balance, and function, providing an adaptive edge that contributed significantly to their prolonged reign. As we continue to explore dinosaur adaptations, the topics of armor, teeth, and claws come into focus, each reflecting another chapter in the story of how dinosaurs equipped themselves for both offense and defense in their richly competitive environments. The symphony of anatomical features, populated by these magnificent creatures, continues to unfold, inviting us deeper into their ancient dominion. As we delve deeper into the remarkable adaptations that allowed dinosaurs to thrive, it becomes clear that their physical armaments, armor, teeth, and claws, played crucial roles in both offense and defense. These features were not only tools of survival, but also testimonies to millions of years of evolutionary innovation, enabling dinosaurs to navigate the ancient world's competitive landscapes with remarkable efficiency. Starting with armor, many dinosaur groups developed a wide array of protective structures to shield themselves from predators and rivals. Among the most iconic armored dinosaurs were the thyreophorans, which included stegosaurs and ankylosaurs. These herbivores evolved extensive body armor composed of osteoderms, bony plates embedded within their skin. In ankylosaurs, these osteoderms fused and formed tough, thickened shields over their backs, flanks, and even tails, which in some species ended with massive clubs used as defensive weapons against attackers. The stegosaurids, famous for their alternating rows of large dorsal plates and spiked tails, used these features for defense and possibly thermoregulation or display. Their plates, composed of vascularized bone, might have functioned to intimidate predators or rivals, while their tail spikes, sometimes called thagomisers, were effective weapons capable of delivering powerful blows. Beyond the armored herbivores, many theropod dinosaurs, primarily carnivores, lacked extensive body armor, but evolved other offensive weapons such as sharp teeth and formidable claws. Their teeth, often serrated and curved, were perfectly adapted to slicing flesh and gripping struggling prey. They exhibited heterodont dentition, meaning their teeth varied in shape, depending on their position in the jaw and dietary needs. For example, the fearsome Tyrannosaurus rex had massive bone-crushing teeth capable of exerting one of the strongest bite forces ever known among terrestrial animals. Smaller theropods like Velociraptor showcased a different approach. Rather than sheer bite force, they relied on agility, sharp, recurved teeth, and dagger-like claws. In particular, one remarkably specialized adaptation was the enlarged sickle-shaped claw on the second toe, a lethal tool used for slashing prey. Fossil evidence and biomechanical studies suggest these claws played a significant role in grasping and incapacitating prey, indicating a sophisticated predatory strategy. In addition to teeth, claws themselves represented versatile tools beyond hunting. Herbivorous dinosaurs, like some iguanodontians, used large thumb spikes for defense against predators. These pointed structures could inflict wounds and deter attackers. Meanwhile, claws also facilitated digging, climbing, or manipulating objects, underscoring their multifunctionality. Pterosaurs, the flying relatives of dinosaurs, evolved different claw adaptations suitable for their arboreal or terrestrial lifestyles, while marine reptiles developed fin-like limbs and specialized teeth to capture aquatic prey, demonstrating the diversity of armaments across reptilian lineages during the Mesozoic. The evolutionary arms race between predators and prey drove continual refinement of these physical weapons. For instance, the appearance of more heavily armored herbivores prompted the evolution of stronger jaws and more effective weaponized tails or claws in carnivores. Conversely, predatory pressures selected for better defensive strategies among herbivores, from improved armor plating to behavioral adaptations like herd formation. Furthermore, the development of tooth replacement systems ensured that dinosaurs maintained effective dentition throughout their lives. Most had polyphyodont dentition, meaning their teeth were replaced continuously, allowing damaged or worn teeth to be renewed. This was critical since many species put significant mechanical stress on their teeth during feeding, especially herbivores processing tough vegetation or carnivores crushing bones. Beyond the physical, ornamentation associated with claws and teeth, such as colorful scaly coverings or feathers, might have played signaling roles in mate selection or territorial disputes, a reminder that these features served multiple functions beyond mere survival tools. In sum, armor, teeth, and claws were vital components of the evolutionary toolkit that enabled dinosaurs to defend themselves, capture prey efficiently, and carve diverse ecological roles. These adaptations reflected an ongoing dialogue between anatomy, behavior, and environment, contributing profoundly to the dinosaurs' ancient dominance. Next, we will explore the evolutionary divergence of dinosaurs into their two great lineages, Saurischians and Ornithischians, a critical branching that would shape the diversity and ecological dynamics of dinosaur communities for hundreds of millions of years. The grand tapestry of dinosaur evolution is woven through two primary lineages that arose early in their history, the Saurischians and the Ornithischians. These two groups diverged in the late Triassic, setting forth distinctly different anatomical, ecological, and behavioral trajectories that shaped the remarkable diversity and dominance of dinosaurs across the Mesozoic era. Exploring these lineages provides a window into the evolutionary pathways that led to the variety of forms, from towering sauropods to heavily armored stegosaurs and swift theropod predators, that fascinated even the ancient world. To distinguish between Saurischians and Ornithischians, scientists rely predominantly on differences in their pelvic structures, a classification framework introduced in the late 19th century. The names themselves, meaning lizard-hipped, Saurischia, and bird-hipped, Ornithischia, refer to the contrasting orientations of the bones making up the hips. The Saurischian pelvis retains the more primitive configuration seen in early reptiles, with the pubis bone projecting down and forward, away from the ischium. This arrangement characterizes the group that includes both the colossal long-necked sauropodomorphs, such as Brachiosaurus and Diplodocus, and the predominantly carnivorous theropods, whose lineage gave rise eventually to modern birds. Saurischians exhibit diverse adaptations, but share this fundamental hip structure. Ornithischians, in contrast, evolved a derived pelvic structure in which the pubis is rotated backward, running parallel to the ischium. This bird-hipped arrangement superficially resembles modern bird pelvises, though birds actually descend from Saurischian theropods, a fascinating twist highlighting convergent evolution. Ornithischians were exclusively herbivorous, encompassing a range of species such as stegosaurs with their iconic plates and spikes, ceratopsians with impressive horns and frills, and ankylosaurs armored with bony plates. Ecologically, these lineages diverged in their niches and behaviors. Saurischians included the massive quadrupedal sauropods, which were unparalleled in size and specialized in high browsing, consuming vast quantities of plant matter. Their enormous bodies demanded efficient respiratory and circulatory adaptations, and their long necks gave them access to foliage unreachable by other herbivores. Theropods, the other branch of Saurischians, were primarily bipedal predators or omnivores. From the small bird-like coelurosaurs to the gigantic Tyrannosaurus rex, theropods displayed a spectrum of hunting strategies, sensory adaptations, and social behaviors. Ornithischians evolved a broad array of herbivorous adaptations, including specialized teeth for grinding tough vegetation, complex digestive systems, and, in many cases, bony ornamentation used in defense or display. Groups such as hadrosaurs developed sophisticated dental batteries that allowed efficient processing of plants, contributing to their widespread success, while ceratopsians wielded formidable facial horns and frills for both defense and social signaling. Behaviorally, some ornithischians are believed to have exhibited social behaviors, including herding and possible parental care, strategies that would enhance survival in a world of predators. The bony armor and weaponry they developed further attest to the evolutionary pressures imposed by predation in Mesozoic ecosystems. Recent advances in paleontology, including cladistic analyses and the discovery of transitional fossils, have enriched our understanding of the evolutionary relationships within these great lineages. For example, early sauropodomorphs transitioned from small bipedal forms to the gigantic quadrupeds they became, illustrating gradual shifts in posture, feeding, and locomotion. The Saurischian-Ornithischian divide also informs discussions about metabolism, growth rates, and reproduction. While these traits vary widely within each lineage, the evolutionary pressures acting on them reflect the different ecological roles and life history strategies these dinosaurs navigated. Importantly, this splitting into two major groups had profound impacts on the diversity of the dinosaur clade as a whole. It permitted parallel expansions into distinctly different ecological niches, reducing direct competition and fostering a rich mosaic of form and function. In sum, the divergence between Saurischians and Ornithischians represents a pivotal moment in dinosaur evolution. Understanding their key anatomical distinctions, ecological strategies, and evolutionary innovations allows us to appreciate the complex panorama of dinosaur life. From the neck-elongated giants that ruled the forests and plains, to the armored guardians and agile hunters that dominated their respective realms. As we advance, examining the intricate dynamics of predator-prey relationships during the Cretaceous period will deepen our insight into these ancient ecosystems, revealing how these two powerful dinosaur lineages interacted and coexisted on the planet's grandest stage. The Cretaceous period, spanning from approximately 145 to 66 million years ago, represents the climax of dinosaur evolution and their ecological reign. It was a time marked by dynamic interactions among an impressive variety of predators and prey, shaping complex ecosystems that thrived across diverse habitats, from lush floodplains to expansive coastal regions. Understanding the delicate balance and fierce arms race between these creatures offers profound insight into how dinosaurs not only survived, but dominated their world. Predators and prey co-evolved in a continuous cycle of adaptations and counter-adaptations, each group driving the evolutionary innovations of the other. Among the apex predators, large theropod dinosaurs were the undisputed rulers. Species such as Tyrannosaurus rex in North America, Giganotosaurus in South America, and Spinosaurus in North Africa exemplified the power, agility, and hunting prowess that allowed them to stand at the top of the food chain. These predators evolved formidable physical traits. Massive skulls with powerful jaws packed with serrated, bone-crushing teeth enabled them to deliver lethal bites. Their strong hind limbs facilitated bursts of speed and agile pursuit, while their forelimbs, in species like T. rex, though small, were muscular and possibly used in grasping. Sensory adaptations, including acute vision and olfaction, helped them detect prey across vast distances, while evidence suggests some may have exhibited complex hunting behaviors, potentially including pack hunting in certain species. The prey in Cretaceous ecosystems was diverse, ranging from the smallest herbivorous dinosaurs to massive sauropods and armored species. Herbivores developed a suite of defenses to evade these predators. Armored dinosaurs like ankylosaurs and nodosaurs were enveloped in thick, bony plates and spikes. The armoring was not merely passive. Some, like the ankylosaur with its clubbed tail, wielded powerful counterstrikes. Other herbivores, such as ceratopsians, bore elaborate facial horns and frills, serving both as defense and intraspecies communication. The horned triceratops could confront predators head-on, using its formidable weapons to deter or injure attackers. Meanwhile, fast-moving hadrosaurs relied on speed and agility, sometimes gathering in herds to confuse predators and reduce individual risk. The predator-prey relationship was not merely physical, but also behavioral. Many herbivorous dinosaurs are believed to have lived in social groups or herds, enhancing vigilance and defense against predators. Synchronous nesting sites, evidenced by fossilized nursery colonies, suggest parental care and group protection for vulnerable young. In response, predators adapted to tackle such social defenses. Theropods developed various hunting strategies, from solitary ambush to coordinated group hunting. Fossilized trackways and anatomical studies hint at complex behavior patterns, including stalking prey and cooperative tactics, though interpretations continue to develop with ongoing research. Beyond dinosaurs, the Cretaceous included a rich assembly of other predators and prey, such as the diverse pterosaur species in the skies and marine reptiles like mosasaurs and plesiosaurs dominating the seas. These groups interacted with terrestrial dinosaurs indirectly, shaping ecosystems as a whole through competition and ecological niche partitioning. The plant life itself influenced predator-prey dynamics. The spread of flowering plants, or angiosperms, introduced new food sources and habitats. This botanical revolution led to changes in herbivore diets, digestive adaptations, and feeding behaviors, indirectly affecting predator strategies. Abiotic factors also played significant roles. Seasonal changes, climate fluctuations, and habitat fragmentation continuously reshaped ecosystems, influencing migration patterns, population densities, and the availability of resources. Such pressures favored flexible and resilient species, on both sides of the predator-prey divide. Fossil evidence paints vivid pictures of these interactions. Healed bite marks on bones signal survival from predation attempts. Fossilized footprints show chase sequences, and preserved gut contents reveal diets. Together, they provide glimpses into the ancient dramas of life and death that defined Cretaceous ecosystems. In sum, the predator-prey dynamics of the Cretaceous were intricate and vibrant, driving evolutionary arms races that honed dinosaur physiology, behavior, and ecology. These interactions ensured a balanced yet fierce natural world in which dinosaurs evolved remarkable adaptations that secured their dominance. Looking ahead, we will explore how dinosaurs grew, reproduced, and lived through environmental challenges, further unraveling the biological strategies underlying their ancient success and resilience. The story of dinosaur dominance over more than 160 million years is not just a tale of colossal size and ferocious power, but also of intricate life histories shaped by growth, lifespan, and reproductive strategies. These biological aspects governed how dinosaurs matured, reproduced, and ultimately sustained their populations. Exploring these strategies provides deep insight into how dinosaurs thrived amid often volatile environments and challenging ecological dynamics. Growth patterns in dinosaurs varied widely across species and lineages, but generally displayed traits that set them apart from many modern reptiles. Bone histology, the microscopic study of bone tissue, reveals that many dinosaurs grew remarkably fast, especially during their juvenile stages. This rapid growth is evident from the presence of fibrolamellar bone, a dense, highly vascularized tissue associated with accelerated metabolism and quick deposition of bone mass. Unlike most modern reptiles, which grow slowly and continue growing throughout life in a process called indeterminate growth, many dinosaurs exhibited a growth pattern more comparable to birds and mammals, where rapid growth was followed by a plateau once adulthood was reached. This pattern, known as determinate growth, suggests that dinosaurs reached maturity reasonably swiftly, which has important implications for survival and reproduction. Faster growth protected juvenile dinosaurs from predation and allowed them to reach sizes that opened new ecological opportunities. Lifespan estimates for dinosaurs vary widely depending on species and size, but some large sauropods may have lived for over a century, whereas smaller theropods and ornithischians likely had shorter lifespans, more akin to large modern birds or reptiles. Growth rings in bones, much like tree rings, help paleontologists estimate ages and shed light on lifespan variability. Reproduction in dinosaurs was another critical factor underpinning their evolutionary success. All dinosaurs were oviparous, laying eggs on land with hard or leathery shells adapted to terrestrial environments. Fossilized nests, eggs, and even embryos have provided compelling evidence of diverse reproductive behaviors and strategies. Nest structures varied from simple scrapes in the ground to carefully constructed mound nests, notably seen in some hadrosaurs and theropods. The arrangement of fossilized nests indicates that many dinosaurs nested in colonies, enhancing protection against predators and environmental hazards. Such communal nesting sites also foster social behaviors, perhaps including parental care. Evidence from bone beds containing juvenile skeletons suggests that parental care may have been more common than previously thought. Some species likely guarded nests or cared for hatchlings after emergence, behaviors that improve offspring survival rates in environments brimming with danger. Clutch size, the number of eggs laid at one time, varied significantly between species. Smaller theropods might lay fewer eggs, investing more in each offspring, while some large herbivores like sauropods laid massive clutches but with less parental investment post-hatching. This diversity reflects different reproductive strategies, balancing quantity with quality of offspring depending on ecological pressures. In addition to egg-laying, some dinosaurs exhibited nesting site fidelity, returning to the same locations across generations, suggesting remarkable behavioral consistency and environmental awareness. This also implies learning and possibly social structures within dinosaur populations. Growth and reproduction were tightly linked to metabolism and environmental factors. Warmer Mesozoic climates and abundant food sources supported rapid growth rates and reproductive output, enabling populations to recover quickly from predation losses or environmental stresses. Seasonal variations may have influenced breeding cycles and juvenile development rates. Sexual maturity in dinosaurs was attained before full physical size was reached, analogous to many modern reptiles and birds. This early reproductive capability meant individuals could contribute genes to the population even while still growing, a strategy that assists population resilience. Intriguingly, studies of varying growth rates and reproductive data across species help explain how different dinosaurs exploited specific ecological niches. For instance, the rapid growth and relatively short generation times of some small theropods may have supported their roles as dynamic predators, while the slow-growing, long-lived sauropods invested in size and longevity as survival strategies. These growth and reproductive strategies forged a balance that allowed dinosaurs to persist over many millions of years, effectively navigating ecosystem fluctuations, competition, and predation. Their success was as much a result of life history adaptations as physical characteristics. With this understanding of how dinosaurs grew and reproduced, the next chapter in their evolutionary tale unveils their remarkable competitive edge over synapsid rivals, mammal-like reptiles, that once dominated before dinosaurs took center stage. This interplay of biology and environment highlights the multifaceted reasons behind dinosaur supremacy on ancient Earth. To fully grasp why dinosaurs rose to unparalleled dominance during the Mesozoic era, it is crucial to understand the biological contest that unfolded between them and their primary competitors, the synapsids. Synapsids, often called mammal-like reptiles, were the dominant terrestrial vertebrates throughout much of the Permian and early Triassic, but eventually ceded prominence to dinosaurs. This complex evolutionary interplay sheds light on the nuanced factors that favored dinosaurs and shaped the trajectory of life on Earth. Synapsids include ancestors of modern mammals, alongside a diverse array of prehistoric species that thrived before and during the early Mesozoic era. Notable synapsid groups, such as the therapsids, exhibited many advanced features, including differentiated teeth suited for processing food more efficiently and increasingly sophisticated jaw mechanics. Many also displayed evidence of hair or proto-hair, suggesting early regulatory adaptation to temperature. However, by the Triassic period, synapsids faced intense competition from archosaurs, the larger reptilian clade that included dinosaurs. Though synapsids had previously dominated terrestrial ecosystems, they gradually declined as archosaurs diversified and expanded into numerous ecological niches. Several key factors contributed to the competitive edge of dinosaurs and their archosaur relatives over synapsids. First, anatomical innovations granted dinosaurs superior locomotion. Unlike many sprawling or semi-sprawling synapsids, dinosaurs exhibited an upright postural stance with limbs positioned beneath their bodies. This arrangement allowed for more efficient, energy-conserving movement, greater speed, and endurance, advantages critical for both predator and prey in dynamic ecosystems. Second, respiratory adaptations in dinosaurs likely outstripped those of synapsids. Dinosaurs developed complex air sac systems akin to those in modern birds, enabling continuous unidirectional airflow across lungs for efficient oxygen extraction. This respiratory efficiency would have supported higher metabolic rates and greater stamina, especially important in the warm, oxygen-variable Mesozoic atmosphere. By comparison, synapsid respiratory systems were less advanced, potentially limiting their aerobic capacity. Third, reproductive strategies may have favored dinosaurs. The oviparous nature of dinosaurs, combined with evidence of nesting behaviors, parental care, and communal nesting sites, improved juvenile survival rates. While synapsids were also egg layers or live bearers depending on lineage, varying reproductive strategies and environmental pressures may have influenced their population dynamics disadvantageously during periods of ecological stress. Fourth, the Mesozoic was marked by climatic upheavals and environmental fluctuations that may have disproportionately stressed synapsids. Dinosaurs' physiological versatility, including possibly higher metabolic rates and more efficient thermoregulation, could have provided resilience amid these changes, facilitating their expansion into vacated niches. Additionally, dietary versatility played a role. Dinosaurs diversified rapidly into carnivorous, herbivorous, and omnivorous niches, supported by specialized dentition and digestive adaptations. While synapsids also exhibited dietary diversity, the evolutionary innovation pace and ecological range of dinosaurs allowed them to exploit resources more effectively. Furthermore, many synapsid groups were larger, slower growing, and less adaptable to rapid environmental or competitive pressures compared to more agile and faster-growing dinosaurs. This difference in life history traits probably affected survival and reproduction rates, tipping evolutionary balance. Fossil records also show that following the Permian-Triassic extinction, synapsid diversity plummeted, leaving significant ecological vacancies. Dinosaurs and their archosaur relatives exploited these opportunities and flourished, illustrating how extinction events can reshape evolutionary trajectories through shifts in competitive dynamics. It is important to note, however, that synapsids were not simply outcompeted in every context. Certain lineages survived and radiated, ultimately leading to mammals, which thrived in the Cenozoic era after dinosaurs' decline. This long-term evolutionary success reflects the underlying strengths of synapsid physiology and adaptability. In summary, dinosaurs' superiority over synapsids arose from a combination of efficient locomotion, advanced respiratory systems, reproductive strategies, metabolic adaptability, and rapid evolutionary innovation. These factors, aligned with shifting environmental conditions, underpinned the dinosaurian ascent to dominance in terrestrial ecosystems. As we transition to our next focus on specialization and diversity during the Jurassic period, this backdrop of biological competition sets the stage for appreciating how dinosaurs evolved into an astonishing array of forms and ecological roles across the ancient Earth. The Jurassic period, spanning roughly from 201 to 145 million years ago, stands as a remarkable epoch in dinosaur history. A time when these ancient reptiles not only recovered from previous extinctions, but flourished and diversified to an astonishing extent. This era marked the blossoming of specialization, ecological innovation, and the proliferation of a multitude of dinosaur species that occupied virtually every conceivable niche on land. Exploring this period reveals how dinosaurs fine-tuned their forms and behaviors, setting new standards of diversity and dominance. At the dawn of the Jurassic, the world was undergoing significant geological and climatic changes. The supercontinent Pangaea was fragmenting further, leading to the creation of new coastlines, shallow seas, and varied regional climates. This geological dynamism fostered isolation among dinosaur populations, which in turn promoted speciation and specialization. Ecosystems diversified, ranging from humid tropical forests to arid inland areas, enabling dinosaurs to exploit a wide array of habitats. Among the most iconic developments of the Jurassic was the explosion of sauropodomorph dinosaurs, long-necked, gigantic herbivores that would become the largest land animals ever to have lived. Early Jurassic sauropods, like the massive Brachiosaurus and Diplodocus, evolved extraordinary adaptations supporting their immense size, such as columnar limbs and sophisticated respiratory systems with air sacs that reduced skeletal weight. These giants specialized in high browsing, consuming vast quantities of foliage from treetops inaccessible to other herbivores, illustrating niche partitioning that minimized competition. Theropod dinosaurs, primarily carnivorous and often bipedal, also diversified extensively. Jurassic theropods ranged from medium-sized agile predators like Allosaurus to smaller, more specialized forms. Their limbs, cranial morphology, and dentition reflected adaptations for hunting various prey, signaling ecological complexity within predatory niches. Some theropods exhibited protofeathers, or filamentous integuments, possibly for insulation or display, indicative of evolving physiological and behavioral traits. Ornithischian dinosaurs, including stegosaurs and early ornithopods, underwent significant diversification during the Jurassic as well. Stegosaurs, recognizable by their distinctive rows of dorsal plates and tail spikes, evolved armor and defensive weaponry that protected them from predators. Ornithopods, or bird-footed dinosaurs, developed sophisticated teeth and chewing mechanisms, allowing efficient processing of the abundant Jurassic flora. The Jurassic also witnessed the emergence of more complex social behaviors. Fossil trackways reveal group movement in some species, suggesting herding or pack behavior, which could have provided protection against predators and increased foraging efficiency. Nesting sites display evidence of parental care and communal nesting in some groups, further underscoring behavioral specialization. Additionally, the development of sensory capabilities advanced. Theropods exhibited keen vision, possibly enhanced by forward-facing eyes for depth perception, aiding hunting proficiency. Olfactory bulbs were well developed, facilitating scent tracking. These sensory refinements reflect the dynamic interactions between predator and prey and the selective pressures driving specialization. Environmental factors of the Jurassic, such as warm, stable greenhouse climates, fluctuating sea levels, and varied plant life, fostered complex food webs. The gradual rise of coniferous forests, cycads, and ferns diversified herbivore diets, promoting dental and digestive specializations. Some dinosaurs may have shifted towards new feeding strategies, such as selective browsing or bulk feeding, reflecting evolutionary adaptation to available resources. The adaptive radiation during the Jurassic set the structural foundation for later developments in the Cretaceous. Specialization included not only physical traits, but also reproductive, metabolic, and behavioral innovations. This period thus exemplifies how dinosaurs actively shaped and responded to their evolving environments to optimize survival. In sum, the Jurassic period was a crucible of dinosaur diversification and specialization. From towering sauropods to fleet-footed predators and armored herbivores, dinosaurs evolved an impressive array of forms and functions that exemplified ecological success. Their ability to refine physical structures, behaviors, and life history strategies enabled them to exploit a wide ecological spectrum and maintain dominance amid growing competition. As our narrative advances, we will examine one of the most awe-inspiring aspects of dinosaurs during this time: their evolution into giants of unprecedented size. Understanding how and why dinosaurs grew so large is essential to appreciating their ecological impact and the limits of terrestrial life. The phenomenon of dinosaur gigantism stands as one of the most awe-inspiring chapters in the history of life on Earth. The sheer scale, grandeur, and diversity of the enormously large dinosaurs, from the towering sauropods like Argentinosaurus, Diplodocus, and Brachiosaurus to the massive theropods such as Spinosaurus and Tyrannosaurus rex, prompt compelling questions. How did dinosaurs grow so large, and why? Unraveling this incredible evolutionary achievement involves exploring physiology, environmental context, and ecological dynamics that interplayed to foster gigantism during the Mesozoic. To begin, the evolutionary trajectory toward gigantism was gradual and multifaceted. Numerous lineages experimented with increases in body size, particularly sauropodomorphs in the Jurassic and Cretaceous, which evolved to become the largest terrestrial animals ever recorded. This trend toward increasing size, known as Cope's rule, may have been driven by selective advantages conferred by large body mass. Why did gigantism evolve? There are several hypotheses regarding the adaptive advantages of enormous size in dinosaurs. One key factor is predator avoidance. Large size reduces vulnerability to predation because few, if any, predators can overpower such massive animals. Additionally, a larger body size increases chances for longevity and reproductive success, as bigger animals tend to have longer lifespans and can store more energy reserves. Gigantism also enabled access to new food resources. Sauropods, with their massively elongated necks, could reach high into the forest canopy, feeding on foliage beyond the reach of other herbivores. This access to untapped vegetation reduced competition for food and allowed these giants to exploit ecological niches unavailable to smaller competitors. Their enormous digestive systems efficiently processed large volumes of plant material, extracting necessary nutrients from fibrous, low-quality plants. Physiological adaptations underpinned these massive sizes. Dinosaur respiratory systems, especially in sauropods and theropods, were highly efficient, equipped with air sacs enabling a bird-like unidirectional airflow that maximized oxygen uptake and helped regulate body temperature. This sophisticated respiration reduced the metabolic cost of breathing and body mass, crucial for sustaining gigantism. Their skeletal structure was also ingeniously adapted to bear colossal weight. Pneumatized bones hollowed with air spaces, lightened the skeleton while maintaining strength and rigidity. Columnar legs with robust joints distributed massive loads effectively, ensuring mobility despite extreme mass. Growth rates contributed to gigantism as well. Fossil bone analysis demonstrates rapid juvenile growth in many large dinosaurs, allowing them to reach great sizes relatively quickly, reducing the vulnerable period as small juveniles prone to predation. This rapid growth required high metabolic rates and abundant food, linking gigantism to the warm and productive Mesozoic environment. Environmental factors played an essential role in facilitating gigantism. The Mesozoic greenhouse climate offered warm temperatures year-round, eliminating the seasonal limitations that modern large vertebrates face. Such stable environmental conditions enabled consistent food availability, particularly in extensive floodplains and coniferous forests that dominated the Jurassic and Cretaceous landscapes. High oxygen levels, while fluctuating, also supported larger body sizes by meeting metabolic and cellular requirements more effectively than lower oxygen concentrations. Ecological dynamics further reinforced gigantism. With fewer large competitors after the Permian-Triassic extinction, large herbivorous dinosaurs could proliferate, and large carnivorous dinosaurs evolved alongside to prey on or scavenge these giants. This predator-prey feedback encouraged continued selection for larger, more powerful forms. Although gigantism offered distinct advantages, it also imposed constraints. Larger animals require more resources, reproduce more slowly, and have longer generation times. Their sheer size limited habitats to those capable of supporting their energetic needs, imposing ecological specialization. In summary, dinosaur gigantism was a complex evolutionary outcome shaped by physiological innovations, ecological opportunities, environmental stability, and evolutionary pressures. This achieved scale bestowed dinosaurs with unmatched commanding presences on Earth's ancient landscapes. As we further explore the global distribution and distinctive habitats of dinosaurs, recognizing gigantism's role helps us appreciate the profound influence these magnificent creatures exerted on Mesozoic ecosystems and the paleontological legacy they left behind. The saga of dinosaur dominance would have been unimaginable without appreciating the vast global stage on which these remarkable creatures lived and thrived. The dinosaurian world order was defined not just by their sheer numbers or diversity, but also by their widespread geographic distribution and remarkable adaptability to an extraordinary range of habitats. From equatorial tropics to polar highlands, dinosaurs thrived across all continents, shaping ecosystems that were both diverse and dynamic. During the Mesozoic era, Earth's geography was profoundly different from today. The early part of this era was dominated by the supercontinent Pangaea, a colossal landmass uniting nearly all present-day continents. This megacontinent provided a continuous terrestrial habitat that facilitated dispersal and migration of dinosaur populations across vast distances. However, the immense size of Pangaea also created varied interior climates, often arid and extreme, fostering specialized adaptations among resident fauna. As the Jurassic and Cretaceous periods progressed, plate tectonics caused the gradual breakup of Pangaea into separate landmasses now recognized as the ancestors of modern continents. This continental drift profoundly influenced the spread and diversification of dinosaurs by creating geographical barriers like oceans and mountain ranges. These barriers promoted allopatric speciation, evolution of distinct species in isolation, and fostered the development of unique dinosaur faunas in different regions. In North America, ecosystems ranged from lush floodplains to semi-arid environments, supporting a rich tapestry of dinosaurs. Well-known theropods like Tyrannosaurus rex and herbivores such as hadrosaurs and ceratopsians thrived here, adapting to seasonal climates and varied vegetation. South America hosted gigantic titanosaurs and agile dromaeosaurs, exhibiting remarkable diversity influenced by slightly different environmental pressures. Africa's dinosaur fauna included gigantic spinosaurids and diverse sauropods, inhabiting riverine and coastal habitats. Asia, too, supported varied ecosystems, including deserts, forests, and river valleys, where feathered theropods and diverse ornithischians flourished. Europe's island archipelagos fostered unique dinosaur communities, as did Australia and Antarctica, which, despite colder climates near the poles, supported dinosaurs adapted to temperate, seasonal conditions. The climatic heterogeneity of the Mesozoic helped shape dinosaur ecology. Tropical regions offered year-round abundance of plants, facilitating diverse herbivore populations. Temperate regions introduced seasonality that may have influenced migration, reproduction cycles, and metabolic adaptations. Polar regions, once thought inhospitable for large reptiles, reveal fossil evidence that some dinosaurs endured extended periods of darkness and cold, indicating physiological and behavioral flexibility. Dinosaurs colonized a wide array of habitats: forest canopies, open plains, riverbanks, coastal regions, and even mountainous terrains. Their physical adaptations reflected these environments: long necks for high browsing in sauropods, powerful jaws, and social hunting strategies in theropods suited for prey-rich environments, armored bodies for defense in exposed habitats. This global spread was not limited just to land. The evolutionary cousins of dinosaurs, pterosaurs, dominated the skies, while marine reptiles like plesiosaurs and mosasaurs ruled the seas, forming intricate connections between terrestrial, aerial, and aquatic ecosystems. The interplay between geography, climate, and biological adaptation created a mosaic of ecosystems, each with unique dinosaur assemblages. This geographic and ecological diversity fundamentally contributed to the resilience and longevity of dinosaur dominance, allowing them to withstand environmental fluctuations and competition. In essence, the dinosaurian world was one of vast scale and complexity. From the equator to the poles, in mountains and marshes, dinosaurs adapted and thrived, painting a picture of life's adaptability and evolutionary ingenuity on ancient Earth. As we move forward, exploring the rise of pterosaurs in the skies and marine reptiles in the oceans will illuminate the broader reptilian dominance during the Mesozoic, highlighting how life expanded across every possible frontier. Alongside the reign of dinosaurs on land, the skies and seas of the Mesozoic era were dominated by other extraordinary reptiles. The pterosaurs in the air, and marine reptiles like plesiosaurs, ichthyosaurs, and mosasaurs in the oceans. Their remarkable rise and diversification during this time reveal the breadth of reptilian adaptation and ecological expansion, painting a vivid picture of life's conquest over 3 dimensions of the ancient world. Pterosaurs were the first vertebrates to achieve powered flight, soaring over Mesozoic landscapes with wings formed by a membrane stretching from their elongated 4th finger down to their body. Emerging in the late Triassic, they quickly diversified throughout the Jurassic and Cretaceous periods into a wide variety of forms, ranging from small, sparrow-sized species to giants like Quetzalcoatlus, with wingspans exceeding 10 meters. This evolutionary leap into the air created new ecological niches for feeding, migration, and reproduction. Airborne mastery gave pterosaurs several advantages. They could exploit food sources inaccessible to terrestrial creatures, fish and squid from coastal waters, insects in the forest canopy, and carrion scattered across landscapes. Morphological adaptations, such as specialized beaks, tooth arrangements, and jaw structures catered to diverse diets, from insectivory and piscivory to scavenging. Their lightweight skeletons, thin bones reinforced with internal strutting, and efficient respiratory systems supported sustained flight and energy-intensive activities. Many pterosaurs exhibited complex social behaviors, including colonial nesting and elaborate crests, likely used for display and species recognition. Feather-like pycnofibers covering some species may have aided in thermoregulation or signaling, paralleling developments seen later among dinosaurs. Beneath the waves, marine reptiles emerged as apex predators in the Mesozoic oceans. Ichthyosaurs, evolving early in the Triassic, resembled modern dolphins in body shape and were swift swimmers, preying upon fish and cephalopods. Plesiosaurs flourished with their distinctive long necks and broad flippers, occupying different marine niches from shallow coastal waters to the open seas. In the late Cretaceous, mosasaurs rose to prominence as formidable marine lizards with elongated bodies and powerful tails, dominating the oceans and preying on a variety of marine fauna, including fish, turtles, and even other marine reptiles. Their evolution signifies one of the most successful aquatic adaptations among reptiles. These marine reptiles exhibited physiological adaptations like limb modification into flippers, streamlined bodies for efficient swimming, and salt-excreting glands to tolerate marine environments. They reproduced via eggs laid on land or gave live birth in water, depending on the group, revealing diverse reproductive strategies suited to aquatic life. Interactions among pterosaurs, marine reptiles, and dinosaurs reflect complex food webs bridging terrestrial, aerial, and aquatic ecosystems. For example, some pterosaurs likely foraged along coastlines, scavenging marine carrion or fishing, while large theropod dinosaurs inhabited the inland margins. The rise of these reptiles was facilitated by the breakup of Pangaea, the greenhouse climate, and abundant marine resources, creating diverse and productive habitats. Their success also highlights convergent evolutionary patterns, as different reptile lineages independently adapted to flight or marine environments. Together, pterosaurs and marine reptiles illustrate the remarkable evolutionary flexibility of reptiles during the Mesozoic, enhancing our understanding of the ancient world's complexity and the intertwined fates of its dominant creatures. Next, we will explore the evolution of plant life and how it profoundly influenced dinosaur diets and ecological roles, further deepening the narrative of Mesozoic life's intricate balance. As we continue to explore the magnificent era of dinosaurs, it becomes increasingly clear that plants played an essential, often understated role in shaping the destinies of these creatures. The evolution of plant life during the Mesozoic era not only molded the landscapes that dinosaurs inhabited, but directly influenced their diets, digestional adaptations, behavior, and ecological relationships. Understanding this botanical progression allows us to appreciate the interdependent dance between flora and fauna that defined so much of Earth's ancient biosphere. In the late Paleozoic and into the early Mesozoic, plant communities were dominated by gymnosperms, seed-producing plants that include conifers, cycads, ginkgos, and seed ferns. Unlike the flowering plants that many of us are familiar with today, gymnosperms reproduce by exposing seeds on cones or other structures, rather than enclosing them within fruits. This predominance of gymnosperms provided a stable and abundant food source for many dinosaur herbivores, but it also set constraints and opportunities that influenced dietary specialization. Early in the Triassic and Jurassic periods, the lush gymnosperm forests covered vast swaths of land. Tall conifers formed extensive canopies, while cycads and ginkgos thrived in understory and swampy regions. These plants often possessed tough, fibrous leaves with high cellulose content and defensive compounds to deter herbivory. Dinosaurs that fed on these plants evolved various adaptations, such as specialized teeth and powerful jaw muscles capable of processing coarse vegetation. One noteworthy adaptation was the development of dental batteries in hadrosaurids, a group of ornithopod dinosaurs. Their teeth were arranged in densely packed rows, continuously replaced throughout life, and designed for grinding tough plant material efficiently. This allowed them to exploit gymnosperm foliage and other plants with high fiber and low nutrient content, effectively turning a challenging food resource into a plentiful dietary foundation. Simultaneously, sauropods, the gigantic, long-necked herbivores, exploited a different feeding strategy. Their enormous size allowed them to browse from the tops of trees, accessing leaves and branches largely beyond the reach of other herbivores. Their small, peg-like teeth were optimized for stripping foliage rather than grinding, relying on a large digestive system to break down vast quantities of vegetation. As the Mesozoic progressed into the Cretaceous, the botanical world underwent a dramatic transformation. The rise of angiosperms, or flowering plants. These plants introduced a wide array of new fruits, flowers, and leaves, dramatically increasing the diversity and nutritional availability of plant foods. Flowering plants, which appeared roughly 130 million years ago during the early Cretaceous, brought not only a greater variety of food, but also new ecological interactions, particularly with pollinators. Their rapid spread transformed many habitats, creating more complex plant communities and allowing the evolution of specialized feeding strategies in herbivorous dinosaurs. This influx of angiosperms likely influenced dinosaur diets substantially. Some dinosaurs adapted to include these more nutritious plant parts, evolving specialized teeth and digestive adaptations to cope with changing food sources. For instance, ceratopsians with their powerful beaks and dental batteries could process flowering plants effectively, while certain hadrosaurs might have diversified their feeding habits to include more angiosperm foliage and fruits. The coevolution between plants and herbivores had far-reaching effects. Defensive adaptations in plants, such as tougher leaves, chemical defenses, or structural modifications like spines and thorns, prompted corresponding evolutionary responses in dinosaurs, evident in the development of robust jaws, complex teeth, and even behavioral changes like selective browsing or migratory feeding. Moreover, the changes in vegetation influenced not only herbivores, but also the entire food web. Carnivorous dinosaurs, for example, were indirectly affected by shifts in herbivore populations and behaviors shaped by the evolving plant landscape. Fossil evidence from coprolites, fossilized dung, provides direct windows into dinosaur diets, revealing pollen grains and plant fibers that track dietary shifts over time. These findings align with broader paleoecological data, showcasing how plant evolution interlaced with dinosaur ecology. In addition, the progression of plant life set the stage for significant ecosystem complexity, influencing soil composition, climate regulation, and nutrient cycling, which in turn affected dinosaur habitats. In essence, the evolution of plants, from the grandeur of gymnosperm forests to the flourish of flowering plants, played a dynamic and integral role in dinosaur survival, shaping what they ate, where they lived, and how they evolved. This intertwined biosphere underscores the importance of considering both flora and fauna in painting a complete picture of life during the age of dinosaurs. Turning from these foundational ecological interactions, the next chapter will explore how dinosaurs communicated, socialized, and perhaps even coordinated behaviors, shedding light on their social structures and the complexities of herd life. Communication and social behavior among dinosaurs open a fascinating window into the lives of these ancient creatures, revealing a complexity that goes far beyond simple survival. Far from solitary wanderers, many dinosaur species likely engaged in intricate social interactions, cooperative behaviors, and group living strategies that played key roles in their evolutionary success. Herding, vocalizations, displays, and other forms of communication shaped their behavior within diverse ecosystems, giving meaning to their dominance and longevity. Evidence for social behavior among dinosaurs comes from multiple lines of inquiry. Fossilized trackways often show clusters of footprints moving in the same direction and at similar speeds, indicating groups traveling together. Early signs of herding. Bone beds containing numerous individuals of the same species, sometimes including juveniles and adults, suggest communal living or cooperative behaviors such as nesting colonies or collective defense. Herding provided several advantages. It increased protection against predators through safety in numbers, enhanced foraging efficiency by sharing information about food sources, and facilitated reproductive success through social cohesion. For example, large sauropods may have traveled in groups to watch for predators, protect the young, and navigate vast migratory routes. Communication within these groups likely involved multiple channels. Visual signals such as coloration, crests, frills, and even feathers served as displays to attract mates, establish dominance hierarchies, or signal warnings. The elaborate crests of hadrosaurs, some connected to nasal cavities, might have functioned as resonating chambers for vocalizations, producing calls that conveyed identity, location, or emotional states. Auditory communication may have been particularly important. Given the evolution of complex respiratory and vocal structures in many dinosaur groups, vocalizations, from low-frequency rumbles to high-pitched calls, could have supported social bonding, coordination within herds, or territorial displays. Some paleontologists speculate that dinosaurs had the capability to produce sounds comparable to modern birds or crocodilians, their closest living relatives. Tactile communication probably also played a role. Physical contact among herd members, whether for reassurance, dominance, or mating, is common in many modern social animals and likely had parallels among dinosaurs. Fossil evidence of healed injuries and worn teeth hints at interactions ranging from combat and dominance displays to nurturing care. Parental care is another facet of social behavior that has gained substantial support. Many species built nests and exhibited nesting site fidelity, returning to the same locations year after year. Fossils of embryos inside eggs and juveniles found near nests suggest that at least some dinosaurs protected and tended their young, enhancing survival rates. This overlap of social cooperation and reproductive strategy marks a distinct shift from more solitary ancestors. The evolution of brain structures, although generally modest in size relative to body mass, reveals advances in coordination, sensory processing, and perhaps social cognition. Areas responsible for olfaction and vision were often well developed, facilitating nuanced interactions within social groups. Behavioral complexity also varied among groups. Small theropods, some feathered and agile, may have operated in packs for hunting. Hadrosaurs and ceratopsians likely lived in herds with complex social hierarchies. Meanwhile, solitary or loosely social species existed depending on ecological demands. Understanding dinosaur communication and sociality enriches our perception of these creatures as vibrant, interactive participants in their ecosystems, rather than isolated predators or herbivores simply meeting survival needs. As we advance, this social story will intertwine with sensory adaptations like vision, smell, and brain power, further illustrating how dinosaurs navigated their complex worlds. These threads combine to portray a vivid, multi-dimensional tapestry of life in the Mesozoic, setting the stage for life's enduring legacy through time. Dinosaurs were marvels not only of physical might and grandeur, but also of sensory complexity and neural capacity. Their senses, vision, smell, and brain power played pivotal roles in how they interacted with their environment, hunted, avoided predators, communicated, and survived across millions of years. As we delve into the sensory world of dinosaurs, we unveil how their perceptual faculties and cognition contributed to their evolutionary success. Vision was among the most crucial senses for many dinosaurs, especially for predatory species requiring acute awareness to detect prey or rivals. Analysis of dinosaur skulls reveals that some theropods possessed large orbits and complex sclerotic rings, indicating well-developed eyes. Features such as forward-facing eyes in certain theropods, including the ancestors of birds, suggest binocular vision with excellent depth perception. This capability was essential for stalking, precision strikes, and judging distance during hunting. Furthermore, the size of the optic lobes in dinosaur brains, responsible for visual processing, was notably large in many species, supporting the importance of sight. Some herbivores had laterally placed eyes, providing a wide field of view to monitor for predators while feeding. This panoramic vision enhanced survival by maximizing environmental vigilance. Smell was another dominant sense. Olfactory bulbs, the brain regions processing scents, were often well developed in theropods and other groups, implying a keen ability to detect odors from long distances. This acute sense of smell enabled predators to track wounded or hidden prey and locate carcasses for scavenging. For many dinosaurs, olfactory cues likely played roles in social communication as well, detecting pheromones or marking territories. Some studies suggest that olfactory capabilities in certain dinosaurs rivaled or exceeded those of modern carnivorous mammals, demonstrating their sophisticated reliance on scent. Herbivorous dinosaurs might have used smell primarily for environmental awareness and social interactions within herds. Brain size and structure varied widely, but dinosaurs generally displayed larger relative brain sizes than many modern reptiles, especially when compared to their body mass. The encephalization quotient, a measure of brain size relative to body size, indicates that some theropods, particularly small carnivores and bird-line dinosaurs, had advanced neural capacities, implying complex behavior, learning abilities, and sensory integration. Notably, the evolution of bird-like brains in coelurosaurian theropods laid the groundwork for advanced flight, sophisticated vision, and vocal communication in birds, their descendants. This lineage exemplifies the progressive enhancement of brain power within dinosaur clades. Additionally, endocasts, natural or artificial molds of brain cavities, offer insights into the layout of neural centers. They reveal well-developed regions for motor control, sensory processing, and balance, allowing dinosaurs to coordinate movement, interpret sensory inputs efficiently, and respond dynamically to their surroundings. Certain dinosaurs likely exhibited social cognition, problem-solving skills, and behavioral complexity that rival that of modern birds and reptiles. Such cognitive sophistication may have supported social behaviors like herding, mating rituals, territorial disputes, and parental care. Evolutionary pressures favored development of sensory and neural systems that enhanced survival and reproduction, sculpting dinosaurs into perceptive and adaptable creatures. Their senses formed the interface between organism and environment, mediating how they found food, avoided danger, and interacted within ecosystems. By understanding dinosaur sensory worlds and brain power, we appreciate the nuanced sophistication underlying their apparent primal nature. These faculties contributed to the resilience and diversity that made them icons of evolutionary achievement. As we proceed, we will explore how dinosaurs adapted to changing environments, showcasing their resilience and responsiveness amidst the fluctuating conditions of the ancient Earth. The next chapter in their enduring legacy. Throughout their long reign on Earth, dinosaurs demonstrated remarkable resilience and adaptability in the face of continual environmental change. From the volatile climates following mass extinctions to the shifting continents and evolving ecosystems of the Mesozoic, dinosaurs navigated a world in flux. Their ability to survive and thrive amid changing conditions was a cornerstone of their evolutionary success. The Mesozoic Era, spanning the Triassic, Jurassic, and Cretaceous periods, was characterized by dynamic shifts in climate, geography, and biodiversity. Early dinosaurs emerged after the catastrophic Permian-Triassic extinction, confronting a fractured world marked by harsh climates and ecological uncertainty. Over millions of years, Earth's environments transformed dramatically. Rising and falling sea levels altered coastlines, continental drift rearranged habitats, and greenhouse conditions fluctuated. Dinosaurs' adaptive capacities allowed them to exploit new ecological opportunities presented by these changes. One critical adaptation was their physiological and metabolic versatility. Many dinosaurs exhibited warm-blooded or mesothermic metabolisms, enabling sustained activity and survival in varying temperatures and oxygen levels. This metabolic flexibility contrasts with most modern reptiles, which rely heavily on environmental temperatures, making dinosaurs more resilient to climatic oscillations. Morphologically, dinosaurs evolved diverse body plans and feeding strategies that matched environmental conditions. Herbivorous dinosaurs diversified their dentition and digestive systems in response to shifts in prevalent vegetation, such as the rise of flowering plants in the Cretaceous. Similarly, carnivorous dinosaurs adapted hunting techniques and physical traits to cope with changing prey availability and competition. Behaviorally, evidence from fossil trackways and nesting sites indicates that many dinosaurs engaged in social behaviors like herding and parental care. Such social structures could mitigate environmental stresses by enhancing foraging success and offering protection against predators or harsh conditions. The ability to migrate and occupy vast geographic ranges is another factor in their adaptability. Fossil evidence shows similar dinosaur species existing across continents that were once joined, suggesting widespread dispersal and ecological plasticity. This mobility allowed dinosaurs to follow favorable climates and resources over time. Environmental shifts also prompted evolutionary speciation and extinction events within dinosaur communities. Periodic volcanic activity, climate cooling or warming events, and habitat fragmentation occasionally caused local or global extinctions. Yet, the broad diversity among dinosaurs helped ensure lineage persistence, as some species adapted or moved while others declined. Importantly, the gradual buildup towards the end of the Cretaceous saw significant environmental turbulence culminating in the Cretaceous-Paleogene extinction event. While this cataclysmic sequence ended the reign of non-avian dinosaurs, their long-term success before that point showcases their resilience through fluctuating conditions. In summary, dinosaurs' evolutionary narrative is one of continuous adaptation, physiological, anatomical, behavioral, and ecological, that enabled them to persist through shifting environments across millions of years. Their story emphasizes the power of flexibility and innovation in the natural world. Our journey now leads us to the ultimate chapter in the dinosaur saga, their dramatic end, and the legacy carried forward by their modern descendants. This transition offers profound lessons on extinction, survival, and the enduring imprint of these ancient giants on Earth's history. The Cretaceous-Paleogene (KPG) extinction event, occurring approximately 66 million years ago, marks one of the most profound turning points in Earth's biological history. This cataclysmic event abruptly ended the reign of the non-avian dinosaurs and reshaped ecosystems on a global scale, ushering in a new era dominated by mammals and other emerging life forms. Understanding the causes, processes, and effects of this extinction event sheds light on the vulnerabilities and resilience inherent in Earth's biosphere. Leading up to the KPG boundary, the Earth's ecosystems were incredibly diverse and dynamic. Dinosaurs had flourished for over 160 million years, with myriad species occupying land, sky, and sea, while flowering plants and insects continued to diversify. Yet beneath this apparent stability, environmental stresses were mounting, including volcanic activity, climate fluctuations, and changing sea levels, all of which gradually altered habitats and life balances. The defining event associated with the KPG extinction is the impact of a massive asteroid or comet, approximately 10 kilometers wide, striking the Yucatan Peninsula in present-day Mexico, creating the Chicxulub crater. This impact unleashed unimaginable energy, releasing heat equivalent to billions of atomic bombs, triggering massive wildfires, earthquakes, tsunamis, and ejecting vast amounts of dust and aerosols into the atmosphere. The aftermath severely disrupted photosynthesis by blocking sunlight, creating a nuclear winter scenario that led to rapid global cooling and collapse of food chains both on land and in the oceans. Acid rain, resulting from atmospheric chemical reactions, further damaged terrestrial and marine ecosystems. Fossil records vividly illustrate the devastating consequences. Dinosaur fossils above the KPG boundary are notably absent, indicating their sudden extinction. Meanwhile, many groups such as non-avian dinosaurs, large marine reptiles, and numerous marine invertebrates vanished, while others like mammals, birds, avian dinosaurs, crocodilians, and certain amphibians survived and eventually radiated into the new ecological niches. While the asteroid impact is considered the primary driver of the extinction, evidence suggests additional contributing factors. Extensive volcanic eruptions in the Deccan Traps of India released massive volumes of greenhouse gases prior to and during the impact event, exacerbating climate stress through prolonged warming, acidification, and environmental instability. The extinction event's selective nature is also notable. Small, burrowing, or aquatic organisms with flexible diets and reproductive strategies were more likely to survive. This pattern emphasizes how life's complexity and adaptability determine resilience. The KPG extinction reshaped evolutionary trajectories, ending the Mesozoic dominance of dinosaurs and enabling mammals to diversify and fill vacated niches. This colossal turnover paved the way for the rise of modern ecosystems and, eventually, human evolution. Reflecting on the end of dinosaur dominance teaches important lessons about extinction vulnerability, the impact of rapid environmental change, and the extraordinary capacity of life to recover and innovate in the aftermath. In the following section, we will examine the legacy of dinosaurs, focusing on the survivors and descendants that connect the ancient past with the living world today, highlighting how this fascinating lineage continues beyond extinction. Though the devastating Cretaceous-Paleogene extinction event brought an abrupt end to the reign of non-avian dinosaurs, their legacy lives on in remarkable and enduring ways. Far from being consigned entirely to the annals of prehistory, the descendants of certain dinosaur lineages not only survived this mass extinction, but went on to evolve into the diverse and vibrant world of modern birds, a testament to the resilience of life and evolution's ever-unfolding story. Among the multitude of dinosaur groups that vanished approximately 66 million years ago, the avian dinosaurs, belonging to the theropod clade, persisted. These creatures, characterized by feathers, lightweight skeletons, and highly developed sensory and neurological systems, were well adapted to their ecological niches and possessed traits that undoubtedly contributed to their survival during extreme environmental upheaval. The origin of birds from small, feathered, carnivorous theropods marks one of the most significant evolutionary transitions in Earth's history. Fossil evidence, including iconic species like Archaeopteryx and many more recently discovered feathered dinosaurs, bridges the morphological and functional gap between their dinosaurian ancestors and modern avian forms. This lineage inherited many dinosaurian traits, including aspects of bone structure, metabolism, and nesting behavior, but also developed novel features suited to powered flight and diverse feeding strategies. Modern birds exhibit astonishing diversity, occupying nearly every habitat on Earth and participating in complex ecological roles ranging from pollinators and seed dispersers to apex aerial predators. This living lineage continuously connects us to Earth's deep past, illustrating the continuity of evolutionary processes despite dramatic extinction events. Aside from birds, the broader legacy of dinosaurs also resonates through the scientific and cultural realms. The study of dinosaurs has profoundly enhanced our understanding of evolution, extinction, ecology, and Earth's history. Dinosaurs inspire curiosity and wonder, bridging science with imagination and enriching popular culture. Their fossils continue to unveil secrets about the ancient world, with new discoveries reshaping scientific paradigms. Moreover, the extinction of dominant dinosaurs allowed mammals to diversify and expand, leading eventually to the rise of humans. Thus, the dinosaur legacy is intricately linked with the evolutionary narrative of life that culminates in the present day. In considering survivors and descendants, we acknowledge that extinction is not an absolute end, but part of a broader cycle of loss and renewal. The dinosaur story encapsulates themes of resilience, adaptation, and the enduring power of life. As we conclude this extensive exploration of dinosaur dominance, it is fitting to reflect on the lessons these majestic creatures offer. Beyond their ancient grandeur, dinosaurs teach us about survival in changing environments, the importance of adaptability, and the delicate balance sustaining life on our planet. These insights remain vital as we navigate the environmental challenges of today and strive to preserve Earth's biodiversity for future generations. Dinosaurs captivate the modern imagination like few other prehistoric creatures, serving as icons of Earth's distant past and as powerful symbols of nature's grandeur and mystery. Their fascinating lives, puzzling extinction, and dramatic resurgence through science have inspired generations of scientists, educators, artists, and enthusiasts alike. Tracing the story of dinosaurs in contemporary culture and scientific discovery reveals how these creatures continue to shape our understanding of evolution, biodiversity, and the dynamic history of life on Earth. Since the first scientifically described dinosaur fossils in the early 19th century, the field of paleontology has rapidly transformed from isolated curiosity into a robust discipline. Early discoveries, such as the colossal bones of Megalosaurus and the more complete skeletons of Iguanodon and Hylaeosaurus, captured public attention and ushered in the term dinosauria, coined by Sir Richard Owen. This growing scientific knowledge sparked imagination, leading to dinosaur depictions in literature, art, and eventually film, embedding dinosaurs into popular culture. In the 20th and 21st centuries, breakthroughs in fossil technology, imaging methods, and interdisciplinary research methodologies revolutionized our understanding of dinosaurs. Discoveries of feathered dinosaurs in China, revealing close kinship between birds and theropods, reshaped views of dinosaur appearance and behavior. Advanced techniques like computed tomography, CT, scanning allow us to peek inside fossilized skulls to study brain structure, while isotopic analyses shed light on metabolism and diet. Modern dinosaur science leverages genomics, biomechanics, and ecology to paint increasingly nuanced pictures of dinosaur biology. Through collaboration across fields, geology, biology, physics, and computer science, the scientific community continues unveiling aspects of dinosaur life once assumed unknowable, such as growth rates, social behavior, and development. Dinosaurs also hold a special place beyond the scientific realm. Museums worldwide attract millions to their dinosaur exhibits, fostering education and wonder. Films like Jurassic Park popularized new portrayals rooted in up-to-date science, influencing generations' perceptions and fueling interest in STEM fields. Yet dinosaurs provoke reflection on broader themes: extinction, climate change, and humanity's place in the evolutionary timeline. Their story emphasizes both life's resilience and fragility, reminding us that all species are subject to change and fate. Today's discoveries continue unabated, with each new fossil find contributing to the rich mosaic of dinosaur history. Technologies such as virtual reality and 3D modeling bring fossils to life, engaging broader audiences and inspiring future scientists. In essence, dinosaurs occupy a unique crossroads where science meets culture, education meets entertainment, ancient past meets modern curiosity. Their legacy fuels continuous exploration of the Earth's history, evolutionary marvels, and the boundless capacity for discovery that defines humanity. As we frame this narrative of dominance and legacy, we turn finally to the lessons dinosaurs impart about life on Earth today. Adaptation, coexistence, and the enduring dance between organisms and an ever-changing planet. The story of dinosaurs spans hundreds of millions of years, a saga marked by resilience, adaptability, dominance, and ultimately, dramatic extinction. As we reflect on the extraordinary reign of these ancient creatures, we uncover lessons that extend far beyond paleontological curiosity, offering profound insights into life on Earth today, its fragility, its dynamism, and our responsibility within this ongoing story. One fundamental lesson is the power and limits of adaptation. Dinosaurs thrived because they evolved innovative biological traits, efficient metabolisms, diverse reproductive strategies, remarkable locomotion, and varied diets that allowed them to exploit a wide range of ecological niches. Their success reminds us that life's capacity for innovation and change is essential to survival amidst shifting environments. Yet, the ultimate extinction of non-avian dinosaurs underscores that no matter how dominant a lineage may become, vulnerabilities exist. Sudden environmental cataclysms, like the Cretaceous Paleogene impact event, can disrupt even the most successful species. This awareness echoes in our present day, where rapid human-driven climatic and ecological changes threaten biodiversity globally. Understanding extinction drivers of the past informs conservation efforts, emphasizing the urgency of sustaining resilient ecosystems. Another insight lies in the interconnectedness of life and environment. Dinosaurs' evolution was intimately tied to geological processes like plate tectonics, atmospheric composition, plant evolution, and climate fluctuations. This intricate web highlights how changes in one domain reverberate through biological communities. Today, similar interdependencies between natural systems are crucial for planetary health, influencing how we approach environmental stewardship. The survival and diversification of avian dinosaurs, modern birds, into a vast array of species further illustrates life's tenacity and adaptability. From ancient origins emerge new forms, thriving in environments that have undergone profound change. This continuity encourages a hopeful perspective on life's enduring nature, even amid disruption. Moreover, the extensive fossil record of dinosaurs enriches our scientific methodologies, highlighting the importance of interdisciplinary research, continual inquiry, and humility before the complexity of natural history. Science grounded in evidence, open to revision and discovery, equips us better to understand and respond to contemporary global challenges. Finally, dinosaurs inspire in us a sense of wonder and curiosity, qualities essential for nurturing respect for the natural world and motivating actions toward sustainable coexistence. Their story is a powerful narrative of life's dynamism and the delicate balance sustaining it. In summary, the lessons of dinosaur dominance and their eventual fall offer timeless reflections, celebrate adaptability, respect ecological interconnections, prepare for unpredictable changes, and cherish the richness of life itself. These insights forge a guide as humanity navigates the future, reminding us that our choices shape the legacy we leave on Earth's ever-evolving story.